The Big Bang isn't the beginning of everything. It's the edge of what our laws can explain, a wall where time itself may have switched on. And yet the universe keeps leaving clues, faint patterns in light and gravity, like fingerprints from a moment we're not supposed to reach. If there was no time, what could before possibly mean, and why does the cosmos still seem to remember something earlier? Imagine a map so complete it can trace every galaxy, yet ends at a blank margin where the ink runs out. In that margin, cosmology becomes detective work, and the evidence is written in the sky. We are going to follow that evidence with discipline because wonder alone does not survive contact with equations. Our instruments do not merely photograph the universe, they timestamp it, tagging each signal with a distance and a delay. When we translate redshifts into expansion, and expansion into a history, the cosmos becomes a record, legible but incomplete. The question is not only what happened at the earliest hot moment we can describe, the deeper question is whether any earlier chapter can be physically defined, or whether the grammar of earlier fails when spacetime stops behaving classically. To find out, we will rewind from the structured present into the young universe's heat, density, and symmetry. We will watch matter and radiation trade dominance, see atoms form and meet the oldest light that still travels freely. Then the trail tightens, because beyond that glow, direct images end, and inference must take over. There, the universe offers indirect witnesses, the abundances of the light elements, the statistical grain of primordial fluctuations, and the way gravity sculpted the cosmic web. We will confront the point where our trusted equations return impossible answers, and where singularity is less a destination than a warning label. In that regime, the simplest story, that everything began in one absolute beginning, stops being a conclusion and becomes an assumption. So we will test the leading prologues modern cosmology dares to propose, an episode of accelerated expansion that prepares the hot beginning, a quantum origin where time is not yet a parameter, and a cosmos that contracts, rebounds, and carries memory across the transition. We will also step into stranger frameworks, where the boundary we call the beginning could be a matching surface, a dual description, or a seam between dimensions. Each proposal will be treated as a hypothesis with a price. It must leave a faint signature, or it must admit that the signature cannot exist. The stakes are not philosophical decoration, they are empirical, because every scenario predicts a different pattern in the relics we can still measure. Subtle twists in the microwave background, telltale departures from perfect Gaussian randomness, and whispers of primordial gravitational waves may distinguish a true prelude from an illusion of language. And we'll be honest about what the universe has not granted us, yet. Cosmic variance, instrumental limits, and the sheer scale of the question will press against every claim, forcing us to separate what is plausible from what is merely poetic. By the end, before the Big Bang will not be treated as a slogan, but as a test of whether time is fundamental or emergent. If there is a prior chapter, we will learn where to look for its fingerprints. If there is not, we will learn why the boundary itself can be the deepest physical statement. In this search, the universe is not silent. It is careful. It answers in statistics, in spectra, and in gravity's slow handwriting across the sky. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will begin by interrogating the word before, then rebuild the early timeline and finally pursue the rival prologues that could have set the stage. Each step narrows to one goal: turn the beginning from a limit of speech into a problem the cosmos can settle. We begin with a question that sounds simple, then breaks language apart. What did the universe look like before the Big Bang? The question carries a hidden assumption, that time existed to host a before, and that the word points somewhere physically meaningful. Cosmologists often answer with a polar riddle. Asking what came before the Big Bang may be like asking what is north of the North Pole. The map ends, not because we failed to walk farther, but because direction itself stops making sense. Yet the comparison is not a dismissal, and it is not meant to mock curiosity. It is a warning label on the word before, a reminder that our grammar can outrun our physics. The Big Bang might mark a boundary in our theories, not the absolute start of reality. This documentary follows that boundary, like a survey team walking to the edge of a charted coastline. We will separate what we can observe from what we can infer, and we will say so out loud. We will name where physics is reliable, where it becomes extrapolation, and where it likely fails. First, we define what the Big Bang model actually claims, because the popular image is misleading. It is not a story of a bomb exploding into empty space, with debris flying outward into darkness. It is a description of space itself expanding, with matter and radiation cooling as the universe grows. A better visual is a stretching fabric, except the fabric is not embedded in anything else. Distances between faraway galaxies increase because the metric of spacetime changes, while galaxies themselves remain held together by gravity. Even the phrase "center of the explosion" does not apply, because the expansion is not from a point inside space. In this model, the beginning is not a point in pre-existing darkness. It is the earliest hot, dense phase that our tested equations can track with confidence. The phrase Big Bang is shorthand for that early state, not a guaranteed origin event. The evidence begins with expansion, and it arrives through the telescope as a quiet mathematical pattern. Galaxies show redshifts that increase with distance, summarized by the Hubble-Lemaitre law. The simplest reading is that space has been stretching, carrying galaxies apart while local structures remain bound. Historically, this was not a single eureka moment, but a convergence of ideas and measurements. Einstein's equations allowed dynamic universes, Lemaitre argued for expansion, and Hubble's distance estimate has made the trend visible. The modern picture is sharper now, built from vast redshift surveys and calibrated cosmic distance ladders. If the universe is expanding now, then it was denser and hotter earlier. Running the clock backward compresses today's cosmos into a smaller, brighter, more energetic state. That backward reasoning is not philosophy, it is a calculation grounded in observation and the well-tested relationship between temperature and expansion. The second pillar is the cosmic microwave background, and it is as close as we have to a baby photograph. It is a faint bath of microwaves coming from every direction with remarkable uniformity. It is the cooled afterglow of a time when the universe was a hot plasma, and light could not travel freely. In that early plasma, electrons and nuclei were not yet bound into stable atoms. Photons scattered constantly off free electrons, so the universe was opaque like the interior of a star. The moment the cosmos cooled enough for electrons to bind with nuclei is called recombination, although it was the first combination. When atoms formed, photons decoupled and streamed outward, and the universe became transparent. Those photons still travel through expanding space, their wavelength stretched into microwaves. The CMB is not a picture of the beginning, but it is a snapshot of the universe at about 380,000 years. On screen, the CMB looks like static, but it is structured static. Tiny temperature variations at the level of tens of microkelvin map slight density differences in the early universe. Those differences are the seeds of everything that later became a galaxy, a cluster, and eventually the chemical elements in our bodies. The third pillar is primordial nucleosynthesis, a nuclear clock embedded in the lightest elements. In the first minutes, temperatures and densities allowed light nuclei to form. The predicted ratios of hydrogen, helium, and traces of deuterium and lithium match what we measure across the cosmos. This is not just a qualitative match, and it is not adjustable at will. The key input is the baryon to photon ratio, and the outputs are element abundances that can be checked in ancient gas clouds. Deuterium is especially telling, because stars destroy it rather than create it in bulk. These abundances are a fossil record written in chemistry. They tell us the early universe was hot enough for nuclear reactions, then cooled quickly as expansion diluted it. They also tell us that most matter was not made in stars but inherited from that early phase. The fourth pillar is structure, which is where smoothness and complexity meet. The universe is smooth on the larger scales, yet filled with galaxies, clusters, and filaments. Tiny variations in the CMB map the seeds that later grew under gravity into the cosmic web. As the universe expanded and cooled, dark matter, whatever its microscopic identity, began clumping early because it did not interact with light. Ordinary matter fell into those gravitational wells, heating, shocking, and eventually forming stars. The result is a cosmic architecture that looks almost biological, with nodes, strands, and voids. Together, these pillars form a strong case for a hot Big Bang history. Expansion, afterglow, light elements, and seeded structure converge on one narrative. The model is not a guess. It is a framework repeatedly cross-checked by independent measurements. But the pillars do not answer the word before. They describe an early chapter, not necessarily the first page. To press earlier, we must ask what our equations mean when pushed to extremes, and what it means for time to be part of the system. General relativity changes the rules of time in a way that is easy to say and hard to absorb. Time is not an external clock ticking outside the universe. Time is part of spacetime, shaped by matter and energy, and intertwined with the geometry of space. In everyday life, we treat time as a background river that flows no matter what. In relativity, the flow depends on motion and gravity, and the now of one observer need not match another. That flexibility is not a trick of perception, it is built into the structure of the theory. In relativity, asking what happened before can fail if time itself has an edge. If spacetime has a beginning, causal language can become undefined, like asking for a location beyond the boundary of the map. The question may be ill-posed, even if our curiosity is reasonable. When we extrapolate the Big Bang model backward, densities rise and curvature increases. Eventually the equations predict a singularity, a point where quantities blow up and the theory stops giving meaningful answers. Most physicists treat that singularity as a sign of missing physics, not a literal event we can trust. A singularity is less a place in nature than a warning sign in mathematics. It says our model has been pushed beyond its domain, like using a map of city streets to navigate the ocean. The equations do not merely become difficult, they stop defining distances, times, and energies in a coherent way. The missing physics is quantum gravity, and its absence is the central tension behind the word before. At extremely early times, quantum effects of spacetime itself should matter. Our current theories split the world into general relativity for gravity and quantum mechanics for the small, and the split becomes intolerable near the beginning. Quantum mechanics tells us that fields fluctuate, even in their lowest energy states. If spacetime is also a field-like entity, then its geometry should fluctuate too, producing a foamy probabilistic structure. In that regime, the smooth spacetime of relativity may be an approximation, not a foundation. There is a named boundary for this ignorance, and it is not chosen for drama. Around 10^43 seconds after the extrapolated start, the Planck time, energies approach the Planck scale. At that scale, classical spacetime may not exist as a smooth stage, and the concept of time may be emergent. To picture this, imagine zooming in on a calm ocean until the surface is no longer a surface. At some magnification, waves become molecules, and the idea of a continuous sheet breaks down. The Planck era may be that kind of zoom limit for space and time, so Chapter 1 sets the rules of the mystery. We can observe back to the CMB and infer earlier conditions using tested physics. We can model earlier still, but as we approach the Planck era, confidence collapses and speculation begins. Yet the universe itself adds tension, because the data look oddly prepared. The CMB is astonishingly uniform across regions that seem too far apart to have exchanged signals in a simple Big Bang. The geometry appears close to flat, balanced near a critical density that seems unlikely by chance. This is the horizon problem in plain language. Distant patches of the sky share nearly the same temperature, even though light could not have travelled between them in the available time. Flatness is another version of the same unease, because small early deviations from critical density should have grown, not stayed delicately near zero. These puzzles are not just aesthetic, and they are not complaints about elegance. They suggest that the early universe had a mechanism that smoothed, flattened, and seeded structure. That mechanism is called inflation, a period of accelerated expansion, proposed to explain the uniformity and flatness, while generating the tiny fluctuations we observe. Inflation says that a tiny region, once causally connected, was stretched to cosmic size. That stretching would dilute curvature the way a balloon's surface looks flatter as it grows. It would also amplify quantum fluctuations into classical density variations, small at first, then later sculpted by gravity. Inflation is a clue, but it is also a doorway, because it raises new questions as quickly as it answers old ones. If inflation happened, what started it, and what ended it? Did it occur once, or does it continue elsewhere, spawning many regions like ours? Inflation also sharpens the question of before. because it reframes the Big Bang itself. Some versions make our hot Big Bang a reheating event after inflation, not the first moment. In that picture, the Big Bang is a transition in the universe's state, not the creation of space-time from nothing. Now the suspects enter, not as answers, but as candidate stories that could replace the singularity. One suspect is an inflationary beginning that is finite in the past, with a start that still demands explanation. Another suspect is eternal inflation, where inflation never fully ends and our observable universe is one bubble in a larger multiverse. Eternal inflation is especially unsettling because it turns our beginning into a local event. In that view, inflation continues in some regions while ending in others, producing pocket universes with different conditions. The idea is speculative, but it is tied to the same inflationary mechanism used to explain our own sky. Another suspect is quantum creation, where the word nothing is carefully defined. In some proposals, the universe emerges from a quantum process, where nothing means no classical space and time, not an empty room. The universe could tunnel into existence or arise from a boundary condition that replaces a classical beginning. A different class of suspects avoids a beginning by replacing it with a bounce. In bouncing or cyclic cosmologies, the universe contracts, reaches a high-density phase, then rebounds into expansion. The hot Big Bang becomes the aftermath of a bounce, and before refers to a prior contracting epoch. A bounce sounds simple, but it must fight familiar gravitational instincts. In general relativity, contraction tends toward collapse, so a rebound usually requires new ingredients, modified gravity, or quantum effects that become repulsive at extreme density. The scientific question is whether such ingredients can be consistent and testable. There are also ekpyrotic and brane scenarios, which keep the focus on smoothing but change the method. In these, our universe is tied to higher dimensional structures, and the Big Bang corresponds to a collision or interaction between branes. The smoothing of the universe comes from a slow contracting phase rather than rapid expansion, and the before is a pre-collision history. Another suspect is conformal cyclic cosmology, which treats the far future as a kind of beginning in disguise. It proposes that the remote future of one universe, stretched and thinned, can be mathematically reinterpreted as the Big Bang of the next. In that view, before is the previous aeon, and the boundary is a conformal rescaling rather than a singular start. Each suspect must face the same judge, which is evidence, and the courtroom is the sky. A pre-Big Bang scenario is not just a story about metaphysics. It must leave potential signatures in what we can measure, especially in the CMB, in the distribution of galaxies, and in primordial gravitational waves. Some signatures would be subtle patterns in CMB polarization, hinting at inflationary gravitational waves. Others would be non-standard correlations, features, or asymmetries that a simple inflation model would not predict. A bounce might leave traces in the spectrum of fluctuations, or in a suppression of power on the larger scales. Even the absence of a signal is information, and it can be surprisingly decisive. If we never detect primordial gravitational waves, some inflation models become less plausible. If we find specific non-Gaussian patterns or unexpected relic particles, we narrow the field of viable beginnings. But we must be careful with the word proof, because early universe science is inference under constraints. The earliest moments may be partially hidden behind cosmic opacity and theoretical limits. Our task is to build a case with converging lines of inference, and to admit where multiple explanations can fit the same data. So the opening question returns with sharper edges, and it no longer sounds merely philosophical. If time is part of space-time, then before may not be a valid coordinate, but if the Big Bang is a phase transition, or a bounce, or a reheating after inflation, then before might refer to a real physical history. This is why the mystery matters, beyond the romance of origins. It tests whether the universe had an absolute beginning, or whether beginnings are artifacts of incomplete theories. It also tests whether our best physics can describe the origin of time, or only the evolution of what time already allows. In the chapters ahead, we will move step by step, and we will keep returning to what the universe actually shows us. We will start from what we can see, then push toward what we can only infer. We will treat the Planck era as a boundary line, then examine which suspects can cross it without contradicting the evidence. For now, we stand at the edge of the word before, listening for meaning in the silence beyond it. The universe looks like it began in fire, yet it also looks like it remembers something earlier. The next chapter follows the strongest clues we already possess, beginning with the afterglow that still fills the sky. We start from the present, because the present is where evidence is anchored and where instruments can be calibrated. The universe is about 13.8 billion years old in the standard cosmological model, and that age is not a casual estimate. It is cross-checked by the expansion history, the cosmic microwave background, and the growth of large-scale structure over time. In practice, those checks come from different kinds of measurements, distances, angles, spectra, and they agree within tight margins. On screen, the modern sky looks calm, but it is saturated with ancient information. The sky still glows with a cosmic microwave background at 2.725 Kelvin, a faint microwave bath that reaches us from every direction. It is nearly uniform, yet it is not perfectly smooth. Those tiny anisotropies are a map of early density variations preserved in light. The CMB is also astonishingly old, arriving from a time when the universe was less than 1 million years old. If we could see microwaves with our eyes, the heavens would look like a softly mottled sphere. The variations are only tens of microkelvin, a contrast so small it sounds negligible. Yet those speckles are the seeds of everything later, including galaxies, clusters, and the web-like scaffolding between them. In the visuals, the mottling subtly sharpens, as if the universe is showing us its earliest fingerprints. To rewind the cosmos, we use expansion as a clock, because expansion leaves a measurable imprint on light. Light from distant galaxies is redshifted because space has stretched while it travelled, lengthening its wavelength during the journey. Redshift is not just a Doppler effect from motion through space, because it tracks the growth of the metric itself, space changing while photons are in flight. The farther the galaxy, the longer the path, and the more the wavelength is stretched by that accumulated history. When we point a spectrograph at a galaxy, we see familiar atomic lines shifted toward the red. Those lines act like barcodes, letting us measure redshift with precision and compare many objects. We also see how clean the physics is, because the same quantum transitions appear everywhere, only displaced in wavelength. The deeper point is conceptual. The universe is not merely expanding into emptiness, it is expanding in its own geometry. Cosmology encodes that growth with the scale factor, ET, a compact symbol that carries the universe's changing size. Today, AT is defined as 1 by convention, and earlier it was smaller by a factor set by redshift. When AT halves, wavelengths double, and radiation cools in a precise way that can be calculated, that simple bookkeeping turns spectra into a timeline, and it lets us translate redshift into temperature and density. That cooling is not a metaphor, because it is thermodynamics applied to an expanding spacetime. The energy of each photon drops as its wavelength stretches, and the overall radiation temperature falls in step. This is why the CMB, once a brilliant glow, is now a cold whisper in the microwave band. In the imagery, the early universe shifts from blinding white to ember red to invisible, as the spectrum slides beyond human sight. Matter and radiation dilute differently as the universe expands, and that difference is one of the simplest, most powerful rules we have. Matter density falls like AT to the -3, because particles spread through volume as space grows. Radiation falls like AT to the -4, because each photon also loses energy to redshift, adding an extra factor. That extra factor sounds small, but over cosmic time it reshapes which ingredient controls the expansion. That extra factor is why the early universe was radiation-dominated, even though matter dominates today. Rewind far enough and radiation inevitably takes over, because it rises faster as a T shrinks. In that regime, the universe's expansion rate is set mainly by relativistic energy, not by the mass of atoms. It's a world where pressure matters almost as much as density, and where light itself gravitates. This scaling turns the universe into a laboratory we can run backward, at least in principle. If we know today's contents, we can infer earlier temperatures and densities, and we can estimate when key transitions occurred. The method is powerful, but it depends on assuming known physics still applies, even under conditions we cannot reproduce on Earth. That assumption is not blind faith, because it is repeatedly stress-tested wherever we can compare predictions with data. The first major observational wall is not the beginning, but the moment the universe became transparent to light. Before that, photons scattered constantly off free electrons in a hot plasma, making the cosmos opaque like the interior of a star. After that, light could stream freely and carry a snapshot to us across billions of years. The shift is so decisive that it draws a sharp line between direct imaging and inference. That transition is recombination, about 380,000 years after the hot beginning, when the universe cooled enough for stable atoms. Electrons bound to nuclei and neutral hydrogen and helium formed in large numbers. Photons decoupled from matter and became the CMB we measure today, stretched into microwaves by expansion. The temperature then was roughly a few thousand Kelvin, hot enough to glow like a filament, yet cooling fast. The word recombination is historical, borrowed from laboratory plasmas, but the physics is precise. It is governed by atomic binding energies, the density of baryons, and the flood of photons that can reionize atoms. Even after neutral atoms began forming, residual ionization lingered, because the photon-to-baryon ratio is enormous. In other words, the universe had far more photons than atoms, so a small high-energy tail kept matter slightly ionized. Recombination is also called last scattering, because it marks the last time most CMB photons interacted strongly with charged particles. The CMB is therefore a time machine with a fixed look-back limit, an image plane wrapped around us. It shows the surface of last scattering, not the first moment, and that distinction matters. When we say, we see the early universe, we mean we see the last moment it let light travel unimpeded. On screen, that surface is not a literal shell you could fly to, because it is defined by time, not by distance. Wherever you stand in the universe, you would see your own last scattering sphere centered on you. The CMB is a cosmic horizon drawn by physics, not a boundary wall in space. The camera can drift through galaxies and still keep that sphere centered, reinforcing the idea that it is a time boundary. Between recombination and the first stars, the universe entered the cosmic dark ages, a phrase that is descriptive rather than dramatic. Gas was mostly neutral hydrogen and helium, cooling as expansion continued and as radiation energy thinned out. There were no luminous objects yet, so the universe was dark in visible light, even though it was full of matter. It was not empty darkness, but a quiet, cooling medium waiting for gravity to amplify small differences. In visuals, the Dark Ages are a slow-motion drift of cold gas through an expanding black canvas. The only light is the fading afterglow of the CMB, sliding to longer wavelengths as time passes. It is a universe with structure beginning, but without lanterns. If we could tune our eyes to radio frequencies, we would watch the background dim and redden as the scale factor grows. Gravity still worked during the Dark Ages, and small overdensities grew under its pull. Dark matter clumped first because it did not couple to radiation and could begin collapsing earlier. Ordinary gas fell into those potential wells and began to heat and compress, turning gravitational energy into thermal motion. In the imagery, invisible dark matter forms a skeletal framework, and the gas follows like mist settling into valleys. Those early overdensities were tiny, but they were not arbitrary. Their statistical pattern is written into the CMB anisotropies, which act as initial conditions for later structure. In that sense, the CMB is not only a photograph of the early universe, it is also a blueprint. The blueprint is probabilistic rather than engineered, but it is still predictive, and simulations begin from that pattern. Around 100 to 200 million years after the beginning, the first stars ignited inside the densest pockets of gas. Their ultraviolet light began rionizing the surrounding hydrogen, stripping electrons back off atoms. That process gradually ended the Dark Ages and made the intergalactic medium ionized again, changing how light traveled through space. In the visuals, isolated points of light appear, then carve out expanding bubbles, like embers burning holes in fog. The first stars were likely different from most stars we see today. With almost no heavy elements to help gas cool, early star-forming clouds may have produced very massive stars with short, violent lives. Their radiation and supernovae began enriching the cosmos with the first metals, setting the stage for later generations. The first heavy elements were not a detail, they were a new cooling channel that changed how efficiently gas could fragment. Reionization is not a single moment, but an extended era with patchy bubbles of ionized gas expanding and merging. It leaves signatures in CMB polarization, because scattering off free electrons imprints a subtle pattern. It also appears in absorption features along quasar sightlines, where neutral hydrogen leaves a telltale forest of lines. Each method is indirect, yet together they outline a coherent history of when the universe lit up again. These measurements tie early star formation to a timeline we can test, and they connect astrophysics to cosmology. When did the first luminous objects turn on, and how quickly did they transform their environment? The answers are constrained by data, not only by simulations. Even the uncertainties are useful, because they tell us which physical processes dominate the error budget. Now we rewind past the first stars and past recombination, into a universe that was hot and opaque again. In this earlier phase, matter and radiation were in tight thermal contact, exchanging energy constantly. The cosmos behaved like a near-perfect fluid in thermal equilibrium, a state where temperature is meaningful everywhere. The visuals become a bright, dense haze where photons cannot travel far before being scattered. Thermal equilibrium is crucial because it makes the early universe predictable in a surprisingly simple way. At high temperatures, reactions happen rapidly compared to expansion, so particle populations track the temperature closely. Particle species appear and disappear according to temperature and available energy, as if the universe were a furnace with adjustable heat. In a plain language sense, the universe keeps rebalancing itself faster than it changes. As the universe expands, it cools, and reaction rates eventually fall behind the expansion rate. When that happens, processes freeze out and leave relics, because the universe can no longer maintain equilibrium. The universe keeps a memory of those freeze-outs in particles and abundances, like fossils embedded in a cooling rock. The key is that expansion is relentless, so even strong interactions can lose the race when densities drop. A key idea here is the competition between two clocks. One is the microphysical interaction rate, set by cross-sections and particle densities. The other is the Hubble expansion rate, which sets how quickly conditions change, and freeze-out happens when expansion wins. This is not just a metaphorical contest, because both rates can be written down and compared at each temperature. One relic is the cosmic neutrino background, an ocean of neutrinos that should still fill space. Neutrinos interacted frequently at very high temperatures, then decoupled when the universe was about 1 second old. They still stream through us today, but they are extremely difficult to detect directly, because they interact so weakly. In the visuals, they are suggested by faint, ghost-like trajectories passing through everything, indifferent to matter. Even without direct detection, neutrinos leave fingerprints. They contribute to the radiation density in the early universe and subtly change the expansion rate. That influence shifts the CMB peak pattern and affects nucleosynthesis yields, allowing us to infer an effective number of relativistic species. The remarkable point is that a background we cannot yet see can still be weighed by its gravitational influence. Another relic is the pattern of light elements from Big Bang nucleosynthesis, a brief nuclear episode in the first minutes. In that window, protons and neutrons combined into light nuclei, but only while temperatures and densities were high enough. The results depend sensitively on the baryon density and the expansion rate, which makes nucleosynthesis a quantitative test. Historically, this was one of the earliest successes of the hot Big Bang picture, because it predicted helium before precision CMB maps existed. Big Bang nucleosynthesis begins once deuterium can survive, a turning point called the deuterium bottleneck. Earlier, high-energy photons destroy deuterium as fast as it forms, because the radiation bath is intense. When the temperature falls enough, the bottleneck breaks and heavier light nuclei can build quickly. In the visuals, we see a storm of photons thinning just enough for fragile nuclei to persist. This is one of the early universe's most counterintuitive lessons. Even though fusion is favoured at high density, too much heat can prevent stable nuclei from persisting. Cooling does not merely stop reactions, it enables the first durable steps of nuclear assembly. The universe had to become less violent before it could build anything lasting. Helium-4 is the main product of this early nuclear era because it is exceptionally tightly bound. About 25% of baryonic mass ends up in helium-4, with most of the rest as hydrogen. The exact fraction is a quantitative test of early conditions because it depends on the neutron-to-proton ratio when nucleosynthesis begins. That ratio is sensitive to timing, so helium becomes a kind of cosmic stopwatch. That ratio is set earlier, when weak interactions keep converting neutrons and protons back and forth. As the universe cools, those conversions slow and freeze out, leaving a particular neutron fraction. Neutrons then decay with a known half-life, so the timing between freeze-out and nucleosynthesis also matters. A slightly faster expansion would lock in more neutrons, and the helium fraction would rise in response. Smaller amounts of deuterium, helium-3, and lithium-7 are also produced, and each carries different information. Deuterium is especially diagnostic, because stars tend to destroy it rather than create it in bulk. Measuring primordial deuterium therefore pins down the baryon-to-photon ratio with high sensitivity, making it a cosmological yardstick. In spectra, those deuterium lines sit close to hydrogen lines, subtle shifts that demand careful calibration and patient analysis. Helium-3 is more complicated, because stellar processes can both create and destroy it depending on environment. Lithium-7 is a known tension point, because predicted and observed abundances do not perfectly agree. That mismatch could reflect astrophysical processing, systematic errors, or hints of new physics, and even that uncertainty is informative, because it marks where the model is stressed. The lithium problem is a reminder that precision cosmology can be limited by messy astrophysics, not only by theory. These relic abundances are not just historical trivia, because they constrain the early expansion rate. Faster expansion leaves less time for reactions and changes final yields, especially for helium and deuterium. That sensitivity lets nucleosynthesis act as a probe of extra radiation or new particles, even if those particles are long gone. In the visuals, a simple dial labelled expansion rate shifts, and the predicted abundances move in response like needles on an instrument. In the documentary's visuals, these abundances become real scenes. We see spectra from ancient gas clouds, where absorption lines reveal deuterium in a nearly pristine environment. We see helium in low metallicity galaxies, where the chemical history is short enough to preserve a primordial signature. The camera lingers on the thinness of those lines, because cosmology often depends on measuring what is barely there. The CMB provides a second, independent probe of the same early parameters, and it is astonishingly rich. Its anisotropies are not random speckles, because they follow a physical pattern set by fluid dynamics and gravity. That pattern comes from sound waves in the baryon photon fluid, ripples moving through a hot plasma long before atoms existed. In the visuals, density waves pulse outward, compressing and rarefying the glowing medium like slow-motion thunder. Before recombination, photons and baryons were tightly coupled by scattering, mainly through Thomson's scattering off free electrons. Gravity tried to compress overdense regions, while radiation pressure pushed back with a restoring force. The competition drove acoustic oscillations like ringing in a hot plasma, with a characteristic scale set by how far sound could travel. That sound is not air vibrating, but pressure waves in a relativistic fluid, and the analogy is still physically exact. Those oscillations did not have time to ring forever. When recombination happened, the coupling weakened abruptly, and photons streamed away, carrying the pattern with them. The oscillations froze into the CMB temperature map, and into polarization patterns that encode the velocity field of the plasma. Polarization is the extra layer of information, because it remembers not just density, but motion and scattering geometry. The result is a series of acoustic peaks in the angular power spectrum, a plot that looks abstract but is deeply physical. The peak positions and heights encode the universe's geometry and composition, including baryon density, dark matter density, and the overall expansion history. In a sense, the CMB is a Rosetta Stone that translates early universe physics into measurable angles on the sky. Historically, the leap from noise to precision ruler was one of cosmology's great conceptual shifts. The first peak measures the angular size of the sound horizon at last scattering, the maximum distance sound waves could have travelled by that time. Its position shows that spatial curvature is very close to zero, meaning the universe is nearly Euclidean on the largest scales we can test. That is one of the strongest empirical statements we can make about the large-scale universe, and it rests on data, not preference. Visually, we overlay a circle on the sky map showing how a known physical scale becomes a measured angle. The relative heights of the peaks measure matter and baryon densities in a way that is difficult to mimic by other effects. Baryons enhance compressions and change odd and even peak amplitudes, because they add inertia to the oscillating fluid. Dark matter shapes the gravitational wells and affects the overall peak structure, because it clusters without being pushed around by radiation pressure. The peaks are therefore not decorative features, but a diagnostic pattern, like harmonics revealing the shape of an instrument. The detailed peak pattern also tests the spectrum of primordial seeds, the initial distribution of fluctuations. Observations show a nearly scale-invariant spectrum with small deviations, consistent with simple, early universe mechanisms. The fluctuations are also close to Gaussian, meaning they resemble a random field with simple statistics, which constrains how they were generated. In other words, the universe's earliest noise has a recognizable mathematical fingerprint, and it is surprisingly orderly. Historically, this was not always obvious. Early debates about the universe's origin were shaped by limited data and competing ideas, including the steady-state model. The discovery of the CMB in 1965 and the later mapping of its anisotropies by Kobe, W-Map, and Planck turned the hot Big Bang into a precision framework. On screen, we move through archival imagery, horn antennas, early sky maps, then the crisp Planck full-sky mosaic. So far, the rewind is still grounded in direct observation and well-tested microphysics. We can check expansion with redshifts, check recombination with the CMB, and check the first minutes with element abundances. The story is constrained from multiple directions, not built from one dataset, and that redundancy is part of its strength. When different probes agree, it is harder for a hidden systematic error to masquerade as a cosmic truth. But as we push earlier than nucleosynthesis, we rely more on extrapolation. We still use tested particle physics, but we apply it at energies beyond terrestrial experiments, and we must be careful about assumptions. The confidence remains high in broad strokes, yet the error bars widen, and the room for surprises grows. The visuals subtly shift here, from measured maps to more schematic diagrams, signaling that we are leaning more on inference. Rewinding toward the first second, the universe becomes a dense particle soup with a rapidly changing cast. Photons, electrons, positrons, neutrinos and nucleons scatter constantly, and the mean free path is tiny. The temperature is so high that particle creation and annihilation are routine, and empty space is a misleading phrase. Even the vacuum is busy, because energy is constantly being traded between fields and particles. At about 1 second, neutrinos decouple, because weak interactions become too slow compared to expansion. From then on, neutrinos free stream, carrying away information about conditions at decoupling. Shortly after, electrons and positrons annihilate and heat the photons, because their rest mass energy is dumped mostly into the electromagnetic plasma. In the visuals, pairs of particles meet and vanish into flashes, while the photon bath brightens briefly before continuing to cool. That heating helps set the photon temperature relative to the neutrino temperature, leaving a calculable ratio. It is one reason the neutrino background is expected to be cooler than the CMB today. Even without seeing those neutrinos directly, we can test their influence through the CMB and through structure formation. The universe, in effect, kept separate thermometers for different particle families once they stopped sharing heat. Earlier still, around 10 to the -5 seconds, the QCD transition occurs as the universe cools through the scale of the strong interaction. Quarks and gluons confine into hadrons, forming protons and neutrons as stable bound states. Rewinding through that moment restores a quark-gluon plasma state, similar in spirit to what heavy ion colliders briefly create. The key difference is scale. Colliders make tiny droplets, while the early universe was entirely in that phase. The QCD transition is not just a label, because it changes the degrees of freedom available to store energy. It affects the relationship between temperature and expansion, since the energy density depends on how many particle species are effectively relativistic. It may also influence relics in subtle ways, though many details are hard to observe directly and remain an active area of modelling. In the imagery, the plasma's texture changes, as if a fluid is thickening into a new state of matter. At around 10 to the -12 seconds, the electroweak symmetry breaks, reshaping the particle world. The Higgs field acquires a non-zero value and particles gain mass through that mechanism, changing how they interact. Above that energy, electromagnetic and weak forces unify into an electroweak interaction, and the distinction between them disappears. The visuals become more abstract still, with fields represented as shifting layers and symmetry shown as patterns that suddenly choose a direction. These times are not measured with a stopwatch, but inferred from energy scales and the known cooling law. Rewinding raises temperature, and temperature sets which symmetries are restored and which particles behave as effectively massless. The timeline is therefore a translation between cosmic time and particle physics, connecting the very large to the very small. It is one of science's strangest bridges because it lets the sky test ideas born in particle accelerators. On screen, the rewind becomes more abstract here, because there are no atoms or stars to visualize. Instead, we show a seething, translucent plasma, with particle tracks appearing and vanishing in a haze. The narration stays grounded by reminding us that these are not artistic choices, but consequences of thermal physics and known interactions. The camera moves through the plasma as if through weather, emphasizing that early universe is not a place, but a state. This is where the documentary's boundary line begins to sharpen, because the questions change character. The Hot Big Bang model describes a sequence of states as the universe cools, and it does so with impressive consistency. It does not automatically explain why the initial conditions were so special, or why the early universe was set up to be so uniform. The more precisely we measure the smoothness, the more demanding the explanation becomes. Two puzzles summarize that unease, and both are visible in the CMB if you know what to look for. The horizon problem asks why distant regions share nearly the same temperature, even though they appear too far apart to have exchanged signals in a simple, non-accelerating expansion. In a straightforward rewind without new physics, they were never in causal contact, so why do they match so well? The mystery is not that the universe is smooth, but that it is smooth across regions that should have been strangers. The flatness problem asks why spatial curvature is so close to zero today, when curvature should generally grow in importance over time in standard expansion. In ordinary evolution, any early deviation from critical density tends to amplify, making near flatness unstable without a mechanism. The observed near flatness implies an extreme early fine-tuning if nothing intervened, and that is a quantitative statement. It is like balancing a pencil for billions of years and then discovering it was almost perfectly upright at the start. These puzzles are not philosophical because they can be written as numbers. They translate into constraints on the early value of curvature and on the uniformity of initial conditions across regions that later become widely separated. They suggest that the Hot Big Bang began in a state that looks prepared, as if some earlier process smoothed and flattened the stage. The question is whether that preparation was dynamical, inevitable, or the result of deeper laws we have not yet learned. Inflation is the leading proposed mechanism to explain that preparation, and it is framed as a physical process rather than a narrative patch. It posits a brief era of accelerated expansion before the hot, radiation-dominated phase that we model so well. A tiny, causally connected patch would be stretched to cosmic size, carrying its uniformity outward. In the visuals, a small region expands so rapidly that its initial wrinkles are pulled nearly flat. Inflation can make the universe appear flat, because rapid expansion dilutes curvature the way zooming in on a sphere makes a surface look locally flat. It can also solve the horizon problem, because the patch was once small enough to equilibrate before being blown up. In that way, inflation turns special initial conditions into a dynamical outcome, at least within the framework. The elegance is that one mechanism addresses two numerical puzzles at once, using the same physical lever. Inflation also offers a mechanism for the seeds of structure, which is one of its most compelling features. Quantum fluctuations in fields are stretched to macroscopic scales during accelerated expansion, then converted into density perturbations. Those fluctuations become the initial ripples that later grow into galaxies, and their statistical properties can be compared to CMB data. The idea is subtle but simple in plain terms. Microscopic randomness is promoted to cosmic architecture. The CMB's near-scale invariant spectrum is consistent with simple inflationary models, and the observed Gaussianity also matches many inflation scenarios. Yet inflation is a framework, not a single theory with one unique prediction, and different models can produce similar broad outcomes. That is why the search for distinctive signatures, like specific polarization patterns or subtle non-Gaussian features, remains so important. The documentary lingers on this point, because it separates a good explanation from a tested explanation. This is the careful line we must hold, because the documentary is tracing a boundary between reconstruction and conjecture. Inflation explains the conditions at the start of the Hot Big Bang phase we can model well, including the smoothness and the shape of the fluctuation spectrum. It does not automatically explain why inflation started, how it was selected, or what preceded it, and those questions remain open. Even the word field hides unknowns, because we do not yet know which field or why its potential had the right shape. In many versions, inflation shifts the origin question earlier rather than erasing it. The hot Big Bang becomes reheating after inflation ends, when the energy driving inflation is converted into particles and radiation. The word before returns, now aimed at the inflationary era and whatever sets it up, and our confidence depends on how directly that era can be tested. The visuals show a sudden transformation, smooth expansion giving way to a hot particle-filled bath, without pretending we have filmed the cause. Even if inflation occurred, we still face a deeper limit that is not merely observational. As we rewind to higher energies, gravity becomes as strong as other forces, and quantum effects can no longer be ignored. At that point, classical spacetime may stop being a reliable stage, and the familiar idea of a smooth timeline may begin to fail. The unsettling thought is that our most basic coordinate, time, might be emergent rather than fundamental. That limit is the Planck regime, defined by fundamental constants that combine gravity, quantum mechanics, and relativity. The Planck length is about 1.6 times 10 to the minus 35 meters, a scale so small that ordinary distance loses its intuitive meaning. The Planck time is about 5.4 times 10 to the minus 44 seconds, a tick so brief that our usual notion of earlier becomes precarious. These are not arbitrary numbers, but the scales where dimensional analysis says quantum gravity can no longer be ignored. The Planck energy is about 1.22 times 10 to the 19 gigaelectron volts, far beyond any accelerator we can build. At these scales, quantum fluctuations of spacetime itself should matter, not just fluctuations of fields within spacetime. General relativity and quantum field theory cannot both remain unmodified, because they make incompatible demands when pushed to these extremes. In the visuals, the smooth grid of spacetime begins to shimmer, then breaks into a restless, granular suggestion. The Planck regime is not a place we can observe directly with light, because it is earlier than any electromagnetic signal can carry intact. It is also beyond the energies we can reach in accelerators by many orders of magnitude, which limits direct experimental guidance. What we can do is look for indirect traces, subtle consequences that would echo into later observable epochs. The question becomes almost forensic. What kind of beginning leaves fingerprints that survive the universe's later violence? So we arrive at a wall that is both empirical and theoretical, and it is worth naming both sides clearly. Empirically, the CMB is our oldest direct image, and earlier epochs are inferred indirectly through relics and consistency checks. Theoretically, the Planck scale is where our equations stop agreeing on what spacetime is, and where the word time may need a new definition. The wall is not a failure of curiosity, but a boundary condition on what our current tools can justify. Up to this wall, the rewind is a disciplined reconstruction, built from measurements that converge. We use redshift and the scale factor to translate distance into time, and we test that translation across many surveys. We use relics like light elements and the CMB to check the reconstruction against data, and the checks reinforce each other. The confidence here is earned, because it is repeatedly challenged by new instruments and still holds. Beyond the wall, the narration must change its rules, because the evidence becomes less direct and the theory becomes less settled. We can propose candidates for what happened earlier, but we must label them as speculative and distinguish them from tested history. The goal is not to stop asking, but to separate what is constrained from what is plausible, and to be honest about the difference. In the visuals, the timeline fades from crisp labels into softer, uncertain gradients. This separation is the documentary's working definition of honesty, and it is also the scientific method in miniature. The universe gives us a strong, detailed timeline back to fractions of a second, and it rewards careful inference. Then it forces us to admit that the word before may require new physics to even define, because time itself may be part of the quantum system. That admission is not defeat. It is a precise statement about where our models stop being reliable. And still, the data keep whispering that something shaped the beginning, even if we cannot yet describe it fully. The horizon and flatness puzzles point to an earlier smoothing mechanism, whether inflation or something else with similar effects. The near-scale invariant seeds hint at a process that acted before the plasma cooled, imprinting a pattern we can still measure. The mystery is sharpened by success, because the more we explain, the more clearly the remaining gap stands out. So Chapter 2 ends at the boundary where confidence changes character, and where the visuals become more symbolic. We have rewound from galaxies to the CMB, from atoms to nuclei to quarks, and from quarks toward unified forces. Now we stand at the Planck wall, where time itself may become quantum, and where our best theories demand reconciliation. The camera holds on that wall as if it were a horizon at sea, real, visible, and not yet crossable. The central question returns with new precision, and it is not merely poetic. Can the idea of before the Big Bang make physical sense, if time is part of the system we are trying to explain? If it can, then the next step is to ask which prehistories leave testable traces in our sky, and which ones remain forever beyond reach. The documentary invites the viewer to sit with that distinction, because it is where wonder meets discipline. In the next chapter, we follow those traces into the realm of candidate beginnings, staying close to what observations might allow. We will treat inflation, bounces, and quantum creation as hypotheses with signatures, not as conclusions. We will keep the wall in view because it is where language ends and physics must be rebuilt. We ended at the wall where our rewind becomes inference and our equations begin to argue. The sky looks prepared for a hot beginning, yet that preparation itself demands an earlier chapter. In the CMB, the afterglow is almost too calm, an image that feels rehearsed, like a stage already swept. On screen, that calm is not blankness but texture, faint mottling across a sphere of ancient light. The pattern is subtle enough that you could miss it, yet precise enough to measure to absurd accuracy. We are looking at photons released when electrons and protons first combined into neutral atoms. That moment, recombination, happened about 380,000 years after the hot phase began, and the light has been travelling ever since. When cosmologists talk about a prologue, they are not chasing mythology. They are responding to a specific mismatch between what the hot Big Bang explains and what it assumes. The hot phase is powerful, but it begins with conditions that already look arranged. It starts already expanding, already smooth, already close to spatially flat, and already seeded with the right kind of tiny perturbations. Inflation is the most influential proposal for that prologue. It is not the hot Big Bang itself, but a brief era of accelerated expansion that can occur before the universe becomes a hot plasma. The idea entered modern cosmology in the early 1980s, when Alan Guth framed it as a way to fix several stubborn puzzles at once. In the same decade, refinements by Andre Linde and by Albrecht and Steinhardt made the mechanism more flexible. The storyline shifted from a clever patch to a broad framework, one that could be tested against the sky. In plain terms, inflation says space expanded almost exponentially for a tiny fraction of a second. Distances between points grew so fast that a small patch could become larger than our observable universe. The timescale is hard to picture, because it is measured in fractions of a second so small that ordinary intuition cannot grip them. Even the word brief becomes misleading, because the relevant clock is not human time but the expansion rate itself. Visually, imagine a grid drawn on a rubber sheet, then imagine the sheet swelling faster than any ripple can cross it. Galaxies are not racing across the sheet like shrapnel. The sheet itself is stretching, and the grid lines are being pulled apart. If you could paint a single wavelength of light onto that sheet, inflation would stretch it too, turning microscopic scales into astronomical ones. That speed does not violate relativity, because nothing moves through space faster than light. Relativity limits local motion, not the growth of the metric, so space itself can expand faster than light. Light can still be the ultimate local speed limit, even while the distance between distant points grows superluminally. The distinction is technical but crucial. Physics remains well behaved in every small laboratory. To see why, think in terms of neighborhoods rather than continents. In any small region, physics remains special relativistic, with light cones and causal order intact. Inflation changes how those neighborhoods are stitched together across the whole spacetime. It reshapes which regions can influence which others, not by breaking causality, but by redrawing the map on which causality operates. The engine is vacuum-like energy with negative pressure, acting almost like a temporary cosmological constant. In many models, this energy is carried by a scalar field called the inflaton. A scalar field is the simplest kind of field, one number at each point, yet its simplicity can hide enormous dynamical power. In quantum field theory, such fields can store energy in their potential, and that stored energy can dominate the cosmic budget. When we say vacuum-like, we do not mean empty. We mean a state whose energy density does not dilute quickly as space expands. Ordinary matter thins out as volume grows, and radiation thins out even faster because its wavelength stretches. Vacuum-like energy, by contrast, behaves as if the universe keeps paying the same energy cost per unit volume. That persistence is what makes it capable of driving a runaway expansion. A useful label is the equation of state parameter W, defined by P equals W times ρ. For vacuum energy W is near -1, meaning pressure is negative and comparable in magnitude to energy density. Negative pressure sounds exotic, but it is a precise statement about how energy responds to expansion. It says that as the universe grows, the total energy in a moving volume can increase because the field's potential energy remains nearly constant. Pressure is not just pushing on walls, because in general, relativity it gravitates. It contributes to the stress-energy tensor, which tells spacetime how to curve. In a cosmological setting, pressure can either help slow expansion, or, if it is negative enough, drive acceleration. This is one of relativity's counterintuitive moves. The source of gravity is not only mass, but energy, momentum, and pressure. In the Friedmann picture, expansion accelerates when ρ plus 3p is negative. Negative pressure makes gravity effectively repulsive on large scales, so the scale factor speeds up instead of slowing down. The phrase repulsive gravity is shorthand, but the effect is real in the equations. It is not anti-gravity in a science fiction sense, but a change in how the cosmic average responds to stress energy. During inflation, the Hubble rate is roughly constant, so the scale factor grows nearly exponentially. Each e-fold multiplies distances by e, and dozens of e-folds can rewrite the universe's initial conditions. The point is not a specific number, but the sheer capacity to magnify the microscopic into the cosmic. What began as a quantum-sized domain can become the entire observable sky, with room to spare. If we could watch a graph of the scale factor, it would look like a sudden steep cliff. Before the cliff, expansion might be ordinary and decelerating. On the cliff, it becomes a runaway, and then, just as abruptly, it transitions into the hot, radiation-filled era. A good visual is a calm line that suddenly shoots upward, then bends into a gentler slope as radiation takes over. This is why inflation was proposed to solve the horizon problem. Regions that look causally disconnected in a simple hot Big Bang were once close enough to exchange heat and information. The puzzle is not that the CMB is uniform, but that it is uniform across regions that seemingly never talked. It is like finding two distant rooms at the same temperature when the doors were never open long enough for air to mix. In the standard hot Big Bang without inflation, the early universe is expanding and cooling, and light only travels so far. If you draw the pass-like cone of one patch of the CMB, it does not overlap with the pass-like cone of a faraway patch, yet both patches share nearly the same temperature, to 1 part in about 100,000. That near equality is a quantitative shock, not a poetic one. Before inflation stretches them apart, that small patch can equilibrate and become nearly uniform. After inflation, the same uniform patch becomes the entire region we can observe in the CMB. The calm sky becomes less miraculous when it is the stretched remnant of a once-connected neighbourhood. Inflation turns the horizon problem into a question of timing. When did that neighbourhood have time to settle? Inflation also addresses the flatness problem, which is a statement about how unstable near-critical density seems without a mechanism. Rapid expansion drives the curvature term towards 0, pushing omega toward 1. In other words, inflation dynamically steers the universe towards spatial flatness. It does not demand perfect flatness, but it makes near flatness the generic outcome. The logic is geometric rather than mystical. As the scale factor grows, any initial curvature becomes diluted, like a curved surface looking flatter as you zoom in. A sphere can look like a plane if you only see a small enough patch. Inflation is that zoom, performed not by a camera but by the universe itself. In the Friedmann equation, the curvature contribution scales differently from matter and radiation. Without inflation, maintaining near flatness from the earliest times requires exquisite balancing. Inflation changes the bookkeeping, because exponential expansion makes the curvature term fade into irrelevance. The universe can start with noticeable curvature and still end up looking almost Euclidean within our horizon. A third puzzle is the monopole problem, rooted in particle physics phase transitions. Many grand unified theories predict heavy relics like magnetic monopoles that should be abundant without dilution. These relics are not mere curiosities, because their predicted abundance would dominate the universe and contradict what we see. The problem is not that monopoles are strange, but that they are too stable and too heavy to hide. Inflation dilutes any pre-existing relic density by expanding volume enormously. Monopoles and other unwanted relics become so rare that we should not expect to see them today. The mechanism is brutally simple. If you stretch space enough, number densities plummet. In a visual, dots on a grid spread so far apart that the screen looks empty even if it began crowded. So inflation can smooth, flatten, and clean the early universe in one move. That makes it feel like an answer, but its most powerful feature is also its most unsettling. It does not merely erase a messy beginning, it also claims to manufacture the seeds of everything that later grows. Inflation does not only erase structure, because it also creates the seeds of structure. It takes quantum fluctuations, normally microscopic and fleeting, and stretches them to cosmic scales. The same quantum jitter that usually averages out becomes, under inflation, a blueprint. This is where the prologue stops being a repair job and becomes a creative act. The key idea is that quantum fields cannot be perfectly still, even in their lowest energy state. The inflaton field fluctuates, and those fluctuations become variations in the time inflation ends locally. In the language of cosmology, they become curvature perturbations, tiny wrinkles in the geometry itself. Those wrinkles are not added later, they are baked into the expanding spacetime. A useful visual is to imagine inflation as a rising tide that ends at slightly different moments across a vast surface. Where the tide recedes later, that region has expanded a bit more. When the energy finally converts into heat, those timing differences translate into density differences. The map begins as a time delay, then becomes a temperature pattern we can actually measure. Where inflation ends slightly later, the region expands slightly more and ends up slightly denser after reheating. Those density perturbations become the initial conditions for gravitational growth. Over billions of years, gravity amplifies them into the web of galaxies, clusters, and voids. The largest structures in the universe may trace back to fluctuations smaller than an atom, stretched until they became the scaffolding of everything. Inflation therefore predicts a spectrum of primordial curvature perturbations that is nearly scale invariant. Nearly means not exactly, and that small tilt is one of the most important observational handles. A perfectly scale invariant spectrum would give equal power per logarithmic interval in scale, which is an elegant but idealized limit. The real universe, as usual, keeps the elegance but adds a slight asymmetry. The near-scale invariance is not arbitrary. In slow-roll inflation, the inflaton's potential energy dominates, and the field rolls gradually, so the Hubble rate changes only slightly. That slight change imprints a slight preference for larger scales, which is what the observed tilt reflects. In plain language, the expansion is almost steady, but not perfectly steady, and the sky remembers that imperfection. The scalar spectral index NOIS measures that tilt. Observations find NOIS around 0.965, meaning slightly less power on small scales than perfect scale invariance would give. That tiny deviation is a clue, because it encodes how inflation evolved while it was generating the perturbations. It is a number with a narrative inside it, one that links the shape of a potential to the texture of the CMB. That number is not decorative because different inflationary potentials predict different tilts. The CMB has turned inflation from a qualitative story into a family of models under pressure. Some potentials that once looked natural now sit uneasily beside the data, while others remain viable because they predict just the right gentle tilt. The sky is not only confirming inflation's broad strokes, it is editing its details. Inflation also predicts that the perturbations should be mostly adiabatic. Adiabatic means different components fluctuate together, so the pattern is a shared curvature fluctuation rather than separate composition waves. In plain language, it means the universe is lumpy in the same way for photons, baryons, and dark matter. The lumps are in spacetime's geometry first, and in matter only because matter follows that geometry. The alternative would be isocurvature modes, where one component varies while another compensates. Those modes leave distinct signatures in the CMB's acoustic peaks. The data strongly prefer adiabatic initial conditions, which supports the inflationary mechanism. It is a subtle preference, but it is consistent across multiple measurements and multiple experiments. Competing scenarios must reproduce that preference or explain why it is an illusion. This is one reason inflation remains hard to dislodge. It does not merely fit one feature of the sky, it fits a linked set of patterns. When temperature, polarization, and large-scale structure all point the same way, coincidence becomes harder to argue. Another prediction is statistical simplicity, close to Gaussian random fluctuations. Gaussianity means the map is largely described by its power spectrum, with higher-order correlations small. If the initial fluctuations were strongly non-Gaussian, the CMB would show distinctive phase correlations, like a melody rather than static. Instead, what we see is closer to carefully measured noise, with meaning hidden in its statistics. Planck and other measurements find the CMB is very close to Gaussian. That does not prove inflation, but it rules out many alternatives and many exotic inflationary variants. It also constrains how complicated the inflatons' interactions could have been during the slow roll phase. The early universe, at least in this respect, behaved with remarkable restraint. Still, close to Gaussian is not the same as exactly Gaussian, and that distinction matters. Many inflationary models predict tiny non-Gaussian signals with specific shapes, local, equilateral or folded patterns in the bispectrum. So far, the sky has stayed stubbornly quiet, which is informative in its own way. Silence becomes a measurement, and a limit becomes a map of what inflation could have been. Yet inflation's most famous potential signature is tensor modes, primordial gravitational waves. These are ripples in spacetime produced by quantum fluctuations of the gravitational field during inflation. They are not waves travelling through a pre-existing arena, because the arena itself is what fluctuates. In that sense, tensor modes are the most literal fossil of the prologue. Tensor modes leave a distinctive imprint in CMB polarization, especially in B-mode patterns. B-modes are a twisting polarization component that scalar density perturbations cannot easily mimic. The signal is faint, because it is a second-order imprint on a background that is already delicate. Even if the waves were present, the universe has had 13.8 billion years to smear and contaminate the evidence. To picture polarization, imagine the CMB as a field of tiny arrows, each one showing the preferred direction of the light's electric field. Scalar perturbations produce mostly E-modes, which look like radial and tangential patterns around hot and cold spots. Tensor modes can generate a curl-like component, B-modes, that looks like a subtle swirl. On screen, the difference is almost aesthetic, yet it carries information about the energy scale of the very early universe. The search is difficult because foreground dust can create similar patterns. Experiments must separate faint primordial signals from the Milky Way's polarized emission with extreme care. Dust grains align with magnetic fields, and their thermal emission carries polarization that can masquerade as cosmology. The result is that the most ancient signal must be extracted through the nearest clutter. So far, no definitive primordial B-mode detection has survived scrutiny. Current limits constrain the tensor-to-scalar ratio R to be small, pushing many simple high-energy models into tension. In particular, models that predict large field excursions often predict larger R, and those are increasingly squeezed. The absence of a signal is not empty. It is steering theory away from some of its most straightforward options. Those limits matter because R connects to the energy scale of inflation. A smaller R suggests inflation, if real, occurred at lower energy, or in a way that suppresses tensors. It also suggests that the inflaton's potential may be flatter, or that the dynamics may be more subtle than the simplest textbook cases. The prologue, if it happened, may have been quieter than we once hoped. Inflation also predicts a specific relationship between tensor tilt and R in the simplest slow-roll models. Testing that consistency is a long-term goal, because it would link multiple observables to one mechanism. A consistent triangle of evidence, tilt, amplitude, and polarization would be hard to dismiss as coincidence. It would also be a rare moment when quantum theory and gravity speak in the same observational language. Beyond the CMB, large-scale structure provides another arena for inflation's fingerprints. The same primordial spectrum shapes the clustering of galaxies and the distribution of matter traced by lensing. In maps of the cosmic web, inflation's initial conditions are the opening move, and gravity is the long game. What begins as a near-Gaussian field ends as filaments, knots, and voids that look almost biological in their complexity. Surveys measure the matter power spectrum and compare it to inflationary initial conditions evolved by known physics. Agreement is strong on many scales, though nonlinear growth complicates the smallest scales. On small scales, baryonic feedback, star formation, and black hole activity can blur the clean cosmological signal. The challenge is to separate the primordial imprint from the messy astrophysics that comes later. All of this makes inflation look like the best supported pre-hot Big Bang idea we have. But the documentary's central question is not whether inflation is elegant, it is whether it makes before physically meaningful. The word before is simple in daily life, yet cosmology forces it to carry the weight of spacetime itself. When the clock is part of the system, what does it mean to rewind it? To answer that, we must face what inflation actually replaces. In many models, the hot Big Bang is not the start of expansion, but the start of the hot phase after inflation ends. The universe can be expanding long before it is filled with a thermal bath. The bang becomes less an explosion and more a transition, an abrupt change of state. That ending is called reheating, and it is where the inflaton's energy becomes particles and radiation. Reheating fills the universe with a hot plasma, setting the initial conditions for nucleosynthesis and the CMB. It is the moment the universe becomes a furnace, with particle interactions frequent enough to establish a temperature. Visually, the smooth, dark, energy-like field gives way to a bright, seething soup of particles. In some models, reheating is not a single instant, but a process. The inflaton can oscillate around the minimum of its potential, behaving like a condensate that decays into other fields. Those decay products can scatter, thermalize, and eventually create the radiation-dominated universe we usually start with. There can even be a violent intermediate stage, preheating, where resonant effects dump energy into particular modes before true thermal equilibrium is reached. This is why people often say inflation happened before the Big Bang. They mean before the hot Big Bang, before the radiation-dominated era, not necessarily before spacetime existed. The phrase is a translation choice, and it can mislead if we forget what Big Bang is labeling. In this documentary, the distinction matters because our question is about origins, not just about heat. Reheating is also where inflation becomes testable in a different way. The details of reheating affect the mapping between inflationary parameters and the scales we observe today. When we infer what the inflaton was doing, we must track how each co-moving scale left the horizon during inflation and re-entered later. The bookkeeping is delicate because it links a microphysical decay process to a pattern on the sky. If reheating is inefficient or prolonged, the number of E-folds relevant to CMB scales changes. That shifts predictions for NS and R, turning particle physics uncertainty into cosmological uncertainty. The sky becomes a messenger, but the message is encoded through a thermal history we do not fully know. Even the best data can only constrain inflation through the filter of what happened when inflation ended. Now the knife turns, because inflation's success creates new mysteries. If inflation happened, what started it, what kept it going, and what ended it at the right time? A mechanism that can erase initial conditions also tempts us to ask what initial conditions it needed. The prologue, in other words, demands its own prologue. The inflaton is a placeholder name, not an identified particle. We do not know whether it is related to known fields, to the Higgs, to a hidden sector, or to something emergent. Particle physics has many scalars in speculative theories, but nature has been stingy with confirmed fundamental scalars. Even the Higgs, though scalar, lives in a particular framework that does not automatically deliver inflation without additional structure. Even if a scalar field exists, its potential must have a special shape. It must be flat enough for slow roll, steep enough to end, and coupled enough to reheat without spoiling the perturbations. Those requirements pull in different directions, which is why model builders speak of tension rather than mere preference. The potential must also avoid generating too much non-Gaussianity or unwanted relics during reheating. In slow-roll language, the potential's derivatives must be small in the right units. That ensures the inflaton's kinetic energy remains subdominant, keeping W near -1. Yet the potential must also allow the field to reach a region where slow roll breaks, so inflation can stop and the hot phase can begin. The universe must coast smoothly, then brake sharply, without throwing its delicate perturbations off the road. This is not an aesthetic complaint, it is a model-building constraint. Many potentials can be written, but few are embedded naturally in a deeper theory without tuning. When a model needs parameters adjusted to many decimal places, cosmologists become suspicious, even if the model fits the data. The suspicion is not moral, it is practical. Tuned models often signal missing physics. Inflation also has an initial conditions problem. It requires a patch that is smooth enough and dominated by the right energy to begin inflating rather than collapsing or fragmenting. The irony is sharp. Inflation explains why the universe is smooth, yet it may require smoothness to start. If the early universe was wildly inhomogeneous, why would the inflaton ever find a calm region large enough to take over? Some argue inflation is an attractor, meaning many initial states evolve toward inflation. In that view, even a messy beginning can settle into an inflating regime, because the vacuum-like energy quickly dominates. Others argue the required patch is itself improbable, so inflation shifts fine-tuning rather than removing it. The disagreement is partly physics and partly philosophy, because it depends on what counts as a fair set of initial possibilities. The debate depends on how one defines probability in cosmology, which leads to the measure problem. In an inflating space-time, volumes grow without bound, so naive counting makes almost anything inevitable. If every outcome happens somewhere, what does it mean to predict what we should see here? The problem is not that mathematics fails, but that mathematics offers too many ways to count. Different measures give different answers for what is typical, and typicality is what probability is supposed to capture. Without a principled measure, predictions about what we should observe can become ambiguous. The mathematics becomes a mirror, reflecting our choice of cutoff and waiting back at us. It is a reminder that cosmology is not only about dynamics, but also about how we reason from one universe to many possible ones. This is where inflation's shadow lengthens into the multiverse. In many models, quantum fluctuations of the inflaton can keep inflation going in some regions even as it ends in others. The same randomness that seeds galaxies can, in some regimes, also seed new inflating domains. A small upward fluctuation can delay the end of inflation locally, and that delay can create exponentially more volume. If the field fluctuates upward locally, that region inflates longer and produces more volume. Inflation becomes eternal to the future, and possibly to the past in some formulations, though the past question is subtle. The word eternal here is technical, meaning the process never ends everywhere at once. Like a wildfire that keeps finding new fuel, it can keep going even as it burns out in particular places. Where inflation ends, it can create a bubble universe like ours, with its own hot reheating and its own observable horizon. Different bubbles could inherit different low-energy physics, depending on how fields settle. The landscape of possibilities is not a new story pasted on top, but a consequence of allowing multiple vacuum states. On screen, you can imagine a dark inflating background with bright expanding bubbles, each one a separate cosmic island. This is eternal inflation in its simplest narrative. It is not a proven fact, but a possible consequence of the same quantum ingredients used to generate the seeds we observe. The unsettling part is that the mechanism that makes inflation predictive can also make it proliferate beyond direct test. The prologue becomes a generator, producing more chapters than any observer can read. The multiverse is therefore not a separate fantasy bolted onto inflation. It can be an internal prediction of certain potentials and quantum dynamics, which makes it hard to ignore and hard to test. If the theory naturally produces many causally disconnected regions, then our observable universe becomes one sample from a vast ensemble. That raises a quiet question. Are we measuring fundamental necessity, or are we measuring environmental happenstance? Testing becomes difficult because other bubbles may be causally disconnected from us. Still, some scenarios predict possible signatures, like bubble collision imprints in the CMB or statistical anomalies. A collision could leave a circular feature or a subtle modulation, like a bruise in the afterglow. The search is a kind of forensic work, looking for symmetry-breaking scars on a nearly perfect sphere. Searches for such signatures have found no compelling evidence so far. Absence does not kill eternal inflation, but it reminds us that some consequences may lie beyond practical observation. It also forces a discipline. We must separate what inflation suggests from what it demands. A theory can be mathematically fertile and still be scientifically constrained, but only if we insist on clear links to data. Even without other bubbles, inflation raises a deeper question about beginnings. Can inflation be past eternal, or must it have a beginning in time? If inflation is the prologue, did the prologue itself begin, or is it stitched onto an infinite past? The question is not only about duration, but about whether past is even the right word in an extreme regime. The Born-Guth-Vilenkin theorem suggests that spacetimes with persistent expansion are past incomplete under broad conditions. In many inflationary models, that means inflation cannot be extended indefinitely into the past. The theorem is not a model of the beginning, but it is a constraint on how far the inflating description can be trusted. It tells us that somewhere, the classical picture of eternal expansion must hand off to something else. Past incomplete does not automatically mean a classical singularity. It means the inflationary description breaks down somewhere, demanding a pre-inflationary phase or a quantum origin. The boundary could be a regime where spacetime is still meaningful, but classical equations fail, or it could be something stranger. The prologue may have an edge, and that edge may not resemble time as we know it. So inflation may be a prologue, but not the first line. It may require an even earlier stage that sets the inflaton field, the geometry, and the arrow of time. The prologue becomes a doorway, and behind it there is still a corridor. We can walk to the doorway with data, but the corridor remains dim. This returns us to the documentary's opening hook about the word before. Inflation makes before feel more physical, yet it also pushes the boundary to a place where time may be emergent. If time is not fundamental, then before is not a simple ordering. It is a derived concept. We are used to asking what happened earlier, but the deeper question may be what makes earlier meaningful at all. If inflation begins from a quantum process, we must ask what the word nothing means. In quantum cosmology, nothing often means no classical spacetime, not an empty container. That is a hard idea to narrate because language evolved for objects inside time, not for time itself coming into focus. When we say, from nothing, are we describing an origin, or are we describing a limit of description? If inflation begins from a bounce, we must ask how contraction avoids chaos, and how perturbations pass through the high-density phase. If inflation begins from something outside spacetime, we must ask what counts as an explanation. At what point does a theory stop being a story about causes and become a statement about consistency? The boundary between physics and metaphysics is not a wall, but it can feel like one. Inflation also interacts with the arrow of time. A smooth inflating patch has low gravitational entropy, and explaining why such a patch exists can be as hard as explaining the Big Bang's low entropy. The universe's early smoothness is not just a geometric fact, but a thermodynamic one. The clumping of gravity is a route to higher entropy, so a smooth gravitational field is, in a real sense, special. Some proposals use inflation to explain homogeneity, but not the thermodynamic arrow. Others try to link inflationary dynamics to entropy production during reheating, though the deepest issue remains. Reheating certainly creates enormous entropy in ordinary matter and radiation, yet the special initial state of gravity still demands attention. The furnace can explain heat, but it does not automatically explain why the room was so orderly before the fire. So the chapter's conclusion is not that inflation solves the origin problem. It is that inflation turns the origin problem into a sharper, more testable set of questions. It narrows the range of plausible beginnings by forcing them to reproduce what inflation explains so efficiently. Any alternative must still explain the same calm afterglow, the same near-flat geometry, and the same statistical simplicity. We can test the perturbation spectrum, its tilt, its Gaussianity, and its adiabatic nature. We can keep tightening limits on R, search for primordial B-modes, and look for subtle non-Gaussian shapes. Each new constraint is a kind of interrogation, asking the early universe how it prepared the sky. The questions are precise, even when the answers remain elusive. We can also probe reheating indirectly through how it shifts inflationary predictions. Future surveys of large-scale structure and 21-centimeter signals may extend our reach to smaller scales and earlier times. Those signals would sample many more modes than the CMB alone, turning the universe into a richer statistical laboratory. With more modes comes more leverage, because randomness becomes readable when you have enough samples. But the deepest questions remain upstream of the data we currently have. What selects the inflaton? What sets its initial state? And what principle defines probabilities in an eternally inflating cosmos? When the theory produces too many possibilities, prediction becomes a philosophical as well as a scientific task. We are forced to ask not only what is true, but what it means to know. Inflation's shadow therefore falls across the word before. It offers a plausible prologue to the hot Big Bang, yet it refuses to be the true beginning. The better inflation works, the more insistently it points beyond itself. It is like a spotlight that illuminates the stage, while making the darkness behind the curtain feel even deeper. The next mystery is unavoidable. If inflation is a prologue, what wrote the first line, and what does that even mean when time becomes quantum? The sky has given us clues, but it has not given us the opening sentence. In the next chapter, we follow the candidate answers that live beyond inflation's edge. We test quantum creation, bounces, and other prehistories against the same judge, which is the sky. We ended with inflation pointing beyond itself, toward a boundary where time may fail. Chapter 4 asks the most unsettling question, because it attacks the grammar of origins rather than the details. What if the universe did not begin inside space and time? What if space and time are what began? The phrase before the Big Bang assumes a timeline already exists, quietly waiting for events to be placed upon it. In quantum cosmology, that assumption is the first thing put on trial, because time may be part of what must be explained. The goal is not poetry about nothingness, or a mystical blankness beyond language. The goal is a calculational framework that replaces a classical beginning with quantum boundary conditions, and then asks what those conditions predict. To see why this is even thinkable, imagine the visuals slowing down to almost stillness, as if the film itself resists moving forward. A black screen is not enough because black is already a background, already a stage. Instead, we picture the last instance where our equations still work, temperature rising, wavelength shrinking, curvature climbing, until the familiar coordinates begin to lose their meaning. The numbers on the axis blur, and the grid lines that once felt objective start to look like a convenient choice. First, we must clean up the word nothing. In everyday language, nothing means absolute non-existence, the absence of objects, laws, and even possibilities. In physics, nothing usually means a vacuum state of quantum fields, which is a very different claim. A vacuum is not a void. It is the lowest energy state allowed by the theory's operators and symmetries, and it can still be structured. Even the word lowest hides a technical detail. Energy is defined relative to a Hamiltonian, and the Hamiltonian depends on how you slice space-time. In quantum field theory, fields are the primary entities, and particles are excitations of those fields. Remove the particles, and the fields do not switch off, because the fields are the stage and the actors at once. Even in a vacuum, fields fluctuate due to uncertainty relations that limit how sharply certain quantities can be fixed. These are zero-point fluctuations, not optional noise we can average away. They are built into the commutators that define the theory, and they persist even at absolute zero. In more formal language, the vacuum is not an eigen state of field amplitude at every point, because that would require infinite conjugate momentum. A useful way to picture this is as a restless ocean seen from above at night. No boats are on the surface, yet the water still heaves and shivers, because the sea itself cannot be perfectly still. In the quantum vacuum, the waves are transient field excitations, appearing and disappearing within limits set by the uncertainty principle. Virtual particles are not little balls popping in and out, but bookkeeping devices for those fluctuations in perturbation theory. If the camera could visualize it, we would see brief ripples of brightness, patterns that never settle, yet never fully detach into enduring objects. Vacuum also depends on context, and this is where the story becomes more unsettling. The vacuum of one observer can look like particles to another observer in curved space-time, or even in flat space-time if the observer accelerates. The Unruh effect predicts that an accelerating detector sees a thermal bath where an inertial detector sees emptiness. Hawking radiation takes the same warning to a black hole horizon, where the definition of particle depends on the slicing of space-time. The deeper lesson is that particle is not a universal noun, but a relationship between a quantum field and a particular notion of time. Cosmology adds another twist, because the vacuum is tied to the geometry that defines time and energy in the first place. In an expanding universe, what counts as a lowest energy state can change with time, and different choices can lead to different predictions. The expansion stretches modes, mixes positive and negative frequencies, and can turn vacuum fluctuations into real, classical-looking perturbations. So when models say creation from nothing, they rarely mean creation from philosophical emptiness. They mean creation from a state with no classical spacetime, or no classical matter, or both. That nothing can still be described by a quantum state, which is the crucial point. It can still have a wave function, constraints, and allowed histories, even when there is no classical clock to tick. The narration must hold two ideas together. There may be no classical place, and no classical time, yet the mathematics can still define a space of possibilities. The visuals can suggest this by replacing a timeline with a branching atlas of shapes, each one a candidate geometry with its own internal logic. Quantum cosmology is the attempt to apply quantum principles to the universe as a whole. It treats the geometry and matter fields as quantum degrees of freedom, not as a fixed background with quantum stuff on top. It asks for a wave function of the universe, not a trajectory through a pre-existing time. This is conceptually radical and mathematically incomplete, but it is not arbitrary, and it grows out of the same quantization logic used elsewhere. The ambition is almost audacious. Quantize not only the contents of the universe, but the very notion of where and when. Historically, this ambition emerged as general relativity and quantum theory matured into the two pillars of 20th century physics. By the 1960s and 1970s, the singularity theorem suggested classical spacetime could not be the final word about the beginning. At the same time, quantum field theory made vacuum structure unavoidable, and inflation later made early universe quantum fluctuations observationally relevant. Quantum cosmology sits at that intersection, trying to quantize the very arena in which physics happens. In the background is a decades-long tension. General relativity treats spacetime as geometry, while quantum theory treats dynamics as amplitudes. The canonical starting point is the Wheeler-DeWitt equation, developed in the 1960s from the Hamiltonian formulation of general relativity. It is a constraint equation, roughly the quantum version of the Hamiltonian constraint in classical gravity. In its simplest form, it looks like an operator h acting on the wave function equals 0. There is no explicit time parameter in that equation, and that absence is not a typo. The equation is sometimes described as the Schrödinger equation with the time derivative removed, but that description is only a hint, not a derivation. In ordinary quantum mechanics, the wave function evolves with time, and time is an external parameter. In quantum gravity, time is part of the dynamical system, so it cannot be assumed as an external backdrop. The universe is not a system inside a clock. The clock is one of the system's variables, built from matter fields and geometry that must also be quantized. Even the notion of simultaneous becomes a gauge choice, and gauge choices are not supposed to carry physical meaning. This is the famous problem of time, and it is more than philosophical discomfort. If the fundamental equation has no external time, what does it mean to speak of evolution at all? What replaces the familiar Schrödinger equation, and what replaces the idea of an initial state evolving into a later state? The documentary's visuals can underline the point by removing the timeline from the screen, leaving only a landscape of possible geometries. The narrator can linger on the unease. We're used to stories that move, yet the fundamental description may be static. In practice, quantum cosmology often uses mini-superspace models, because the full theory has infinitely many degrees of freedom. Mini-superspace reduces the problem to a few collective variables, like the scale factor that measures the size of the universe in a homogeneous scalar field. This is a drastic truncation, and it risks missing important physics. But it makes the equation solvable enough to interpret, and it can reveal how quantum boundary conditions might work. In the visuals, the infinite dimensional space collapses into a clean diagram, one axis for size, one axis for field value, and a wave function spread like mist. In these reduced models, the wave function is interpreted as assigning amplitudes to different geometries and field configurations. It is not a probability distribution over time because time is not yet a given. It is a weighting over possible classical-looking universes that could emerge in a semi-classical regime. The boundary condition chosen for that wave function becomes the substitute for a before because it selects which histories are allowed. In a sense, the boundary condition plays the role that initial data plays in classical physics, but it does so without a first moment. Two famous boundary conditions dominate this chapter, and they frame the debate with a stark simplicity. Hartley and Hawking propose a no-boundary condition, which tries to remove the edge of the beginning. Vilenkin proposes a tunneling boundary condition, which treats the universe as a quantum event. Both aim to replace a singular start with a quantum origin, but they weight histories differently. Both also reveal a deeper theme. Origins become questions about which mathematical solutions we permit. Hartler. Hawking begins with a technical move that sounds like a metaphor, and the narration must make it feel precise. It uses imaginary time, a Wick rotation that turns time into a spatial-like coordinate by multiplying it by the imaginary unit. In that Euclideanized description, the metric becomes positive definite, and certain singular behaviours can be smoothed. The beginning becomes like a rounded cap rather than a sharp edge, at least in the saddle point approximation. The trick is not a claim that time is literally imaginary, but a calculational continuation that changes which geometries contribute. The no-boundary idea is often explained with a simple analogy, and it remains one of the best visual anchors. The Earth's surface is finite but has no boundary. You can travel north until north stops making sense at the pole, and there is no cliff at the end. In the proposal, early time behaves like a spatial direction that closes off smoothly, so there is no first instant. The camera can glide over a globe-like surface with no seams, then dissolve that surface into a four-dimensional curvature that we can only suggest with light and shading. But the analogy can mislead if we forget what it is standing in for. The Earth's surface is embedded in a higher dimensional space, while the no-boundary proposal does not require an external embedding. The point is not that the universe is a sphere sitting somewhere else. The point is that the geometry can be regular and compact without requiring a boundary where physics must break. What matters is intrinsic curvature, not an external container, an idea general relativity trained us to accept, yet still hard to visualize. In the mathematics, one computes a path integral over compact Euclidean geometries, weighted by the exponential of minus the Euclidean action. The wave function is dominated by saddle points, approximate classical solutions that contribute most to the amplitude. These saddle points are not arbitrary drawings, but solutions of the Euclidean field equations with specific regularity conditions. The result is a weighting for different initial values of the scale factor and fields, a recipe rather than a complete theory. The narrator can add a quiet reminder. Even in this timeless setting, the action still governs what is favoured, because physics keeps its old habits. Visually, we can imagine the camera gliding over a smooth, pale surface that curves gently into itself. There is no corner where the surface begins, only a region where one coordinate loses meaning and another takes over. Then, as the geometry transitions to Lorentzian signature, a direction becomes time-like, and expansion becomes a classical concept again. The birth is not a bang in time, but a change in how geometry is described. The palette can shift from muted Euclidean whites to the darker, sharper contrast of a spacetime with a definite light cone structure. The mysterious part is not the imagery of a rounded beginning. The mysterious part is what it claims about explanation, because it shifts the question rather than answering it. Instead of asking what happened at t=0, it asks which histories are allowed by regularity and by the action. The origin becomes a boundary condition in the space of geometries, and the universe is treated as a quantum superposition of possible beginnings. We are no longer watching a single fuse burn down to a spark, we are waiting an entire library of possible first pages. Vilenkin's tunneling proposal keeps a different intuition, one closer to textbook quantum phenomena. It treats the universe as a quantum system that can tunnel into existence, much as a particle can tunnel through a barrier. Tunneling is the quantum phenomenon where a system crosses a classically forbidden region. Even when classical equations would forbid the trajectory, it does not require a classical path through that region, because the wave function can have support there. The key is exponential suppression, not impossibility, and that distinction is where quantum theory quietly overturns common sense. In cosmology, the barrier is not a wall in space, and it is not a force pushing outward. It is a barrier in configuration space, often phrased in terms of the scale factor and effective potential in mini-superspace. Classically, a universe of zero size cannot expand because there is no space-time to expand within, and the classical equations become singular. Quantum mechanically, the wave function can connect a small scale factor region to an expanding classical region, in the same way a wave function can connect two classically separated regions. The documentary can show this with a diagram that looks deceptively simple, while the narrator stresses that the axes are not ordinary distance. The tunneling boundary condition selects outgoing modes, corresponding to an expanding universe rather than a contracting one. It is a choice about which solutions of the Wheeler-DeWitt equation are allowed, and that choice matters. It is not a movie of something pushing the universe outward. It is a statement about amplitudes and allowed semi-classical branches, where outgoing is defined in the space of geometries. The phrase outgoing is itself a translation, an attempt to borrow directional language from a world where direction already exists. If the no-boundary proposal feels like geometry closing smoothly, the tunneling proposal feels like emergence through a narrow quantum gate. The visuals can show a potential barrier drawn not in ordinary space, but in a schematic landscape labelled by the scale factor. On one side, a region where classical motion is forbidden. On the other, a trajectory that becomes classical expansion, with the wave function's phase guiding a semi-classical arrow. The moment of emergence can be shown as interference fringes tightening into a clean classical-looking wave, as if probability condenses into history. Both proposals face the same interpretive hazard, and the documentary should linger here because it is where certainty dissolves. They use quantum mechanics, but quantum mechanics is usually formulated with external time and external observers. Here there is no external clock and no outside measurement apparatus. The universe cannot be observed from the outside, so the meaning of probability must be handled carefully, and the usual measurement postulates cannot be imported unchanged. The narrator can pose the uncomfortable question: if there is no outside, who or what does the measuring that turns amplitude into experience? Still, these models compute something concrete, and that concreteness is their appeal. They compute relative probabilities for different initial conditions, given a choice of boundary condition and a model for matter content. In inflationary settings, they can weight how likely inflation is to start and how long it lasts. They can also influence predicted curvature and the spectrum of primordial perturbations, which is where contact with data becomes imaginable. Even a small preference in the earliest weighting could, in principle, echo forward into what kinds of universes are common. This is where the chapter reconnects to earlier chapters' evidence, and the sky returns as a laboratory. Inflation's success depends partly on initial conditions, because inflation is not just a mechanism, but a regime that must begin. Quantum cosmology tries to explain why those conditions might be selected rather than assumed. The same CMB that motivates inflation becomes the arena where boundary conditions might leave subtle fingerprints, faint as they may be. The visuals can return to the mottled microwave sky, then overlay it with faint theoretical curves, predictions as thin lines against a noisy cosmos. One key question is the probability of inflation, and it sounds simple until you try to define it. Some treatments of Hartley, Hawking have been argued to favour less inflation, depending on how the measure is defined and how the action is evaluated. Some treatments of tunnelling have been argued to favour more inflation, again depending on measure choices and on the shape of the inflationary potential. The disagreement is not a trivial technicality. It is a sign that quantum cosmology is sensitive to how we define what counts as typical and to what we mean by probability in a single universe. When the sample size is 1, the word likely becomes a delicate instrument. Measures matter because the space of possible universes is not like a jar of marbles. The variables can be continuous, the volume of parameter space can be infinite, and different coordinate choices can distort what looks uniform. Even in classical cosmology, defining a measure on solutions is delicate. In quantum cosmology, the delicacy becomes central because the wave function's normalization and interpretation depend on it. The narrator can slow down here because this is where intuition fails. Changing variables can change what looks like a fair weighting, and fairness is exactly what probability is supposed to encode. Another question is curvature, because curvature encodes the geometry of space on the larger scales. Boundary conditions can weight open, flat or closed universes differently, and those weights can influence what inflation must accomplish. Observations show curvature is very close to zero within our horizon, with only small allowed deviations. Inflation naturally drives curvature towards zero, but quantum cosmology could influence whether inflation begins in a way that makes near flatness likely. The prediction is subtle because inflation can wash out many initial differences, leaving only a narrow window for distinguishable traces. The visuals can show a slightly curved grid gradually flattening, as if expansion irons out the creases of space. A third question is primordial perturbations, the tiny fluctuations that later grew into galaxies and clusters. In the simplest inflationary picture, quantum fluctuations begin in the bunch, Davy's vacuum, which is a particular choice of lowest energy state in an approximately de Sitter background. But the initial quantum state of fluctuations can deviate from that simplest choice, especially if the earliest regime is not well described by standard time evolution. Deviations could imprint features in the power spectrum, like oscillations, phase shifts, or a cutoff on the larger scales. Even a slight non-standard phase at horizon exit could, in principle, change the pattern of hot and cold spots we see today. These effects are hard to disentangle from cosmic variance because the larger scales give us only a small number of independent modes. They are also hard to separate from late-time astrophysical complications, like reionization history and foreground contamination. Yet the possibility remains tantalizing, because it suggests that a boundary condition might leave a statistical scar. The question becomes almost forensic. What patterns could only come from the earliest quantum state? If the universe had a quantum accent at birth, would it still be audible in the oldest light? Now we face the chapter's central conceptual turn. If the Wheeler-DeWitt equation has no time, what becomes of before? The answer is not merely that we do not know what happened earlier. The answer can be that earlier is undefined, because the parameter we call time may not exist in the regime we are trying to describe. The documentary can let that land with a pause, as if the narration itself is deciding whether it is allowed to continue. Time may be emergent, which is a phrase that can sound vague until we specify what it means. It can arise as an approximate parameter that labels correlations between subsystems, once the universe enters a semi-classical regime. In such a regime, one degree of freedom can behave like a clock for the others, because it changes monotonically and can be used to order events. The scale factor or a homogeneous field can play that role, allowing an effective Schrödinger-like evolution for perturbations. In plain terms, time is what a reliable internal variable feels like when it ticks steadily enough. This is sometimes described as relational time, because time is defined by relations among variables rather than by an external master clock. You do not ask what the universe does at time t. You ask how one variable changes when another variable takes a certain value. In a laboratory, we take the clock for granted. In the early universe, the clock may be a collective degree of freedom that only becomes reliable after decoherence and classicality set in. The visuals can show this as two changing patterns. One pattern becomes the ruler by which the other is read. In that view, the universe does not start at a first moment. It enters a regime where a time variable becomes meaningful, and where classical causality becomes a good approximation. Asking what happened before that is like asking what is north of the North Pole, but with higher stakes. It is not a refusal to answer. It is a claim about the domain where the question has meaning, and about the limits of our classical intuitions. The narrator can ask, softly but directly, are we demanding an answer to a question that the universe never posed? The documentary can make this feel less like wordplay, by leaning on visuals of coordinates dissolving. A grid drawn over a surface begins to warp and then fade, until only invariant relationships remain. Then, as the universe grows and cools, the grid reappears, and one direction becomes a reliable time coordinate again. The emergence of time is shown not as magic, but as the return of a useful approximation. The sound design can help too, shifting from a timeless drone to a faint rhythmic pulse as classicality takes hold. Entanglement is often invoked to make this less abstract, because it provides a physical mechanism for classical appearance. Correlations between parts of the universe can define an arrow of time through decoherence, where interactions with unobserved degrees of freedom suppress interference. Decoherence can make different semi-classical histories stop interfering, producing branches that look classical. Observers inside one branch experience a definite past, even if the full state is timeless. The narration can emphasize that decoherence is not a mystical collapse, but a dynamical spreading of phase information into inaccessible degrees of freedom. This does not magically solve the arrow of time problem, and the chapter should not pretend it does. It reframes it, shifting attention to the structure of the quantum state and its correlations. The low-entropy initial condition becomes a statement about the quantum state, and about which degrees of freedom are initially unentangled in certain ways. The emergence of classical spacetime becomes tied to which degrees of freedom decohere, and which remain coherent, and to how robust those branches are. In other words, the arrow may be less about a cosmic clock and more about the architecture of correlations. There is a quiet tension here that is worth naming. Decoherence explains why interference becomes hard to observe, but it does not by itself select a unique outcome. In cosmology, where there is no external observer, the interpretation of branching becomes part of the foundational debate. Yet even without settling interpretation, decoherence can still be used as a practical tool to explain classical behavior and the stability of perturbation spectra. The documentary can show multiple faint histories on screen, then let one thicken into the single history we experience. The chapter now pivots to energy, because creation from nothing triggers an immediate objection. How can something appear without violating conservation of energy? which feels like one of physics' most sacred rules. In cosmology, energy conservation is subtle even before quantum gravity enters, and the subtlety is not a loophole invented for convenience. The narrator can acknowledge the instinct because it is a good instinct. Conservation laws are powerful precisely because they usually survive our mistakes. In general relativity, global energy conservation is not guaranteed in an expanding universe because the relevant symmetry may not exist. There is local conservation of stress energy, expressed by a covariant divergence equal to 0, which means energy and momentum are conserved locally in a curved spacetime sense, but a global conserved energy requires a time translation symmetry, and an expanding universe does not have a global time translation invariance. The redshifting of photons is the simplest reminder that naive energy bookkeeping fails globally, because photon energy decreases as the universe expands. What is conserved is the consistency of the equations, not a single number that stays fixed for the whole cosmos. If we try to ask where that energy went, we discover the question is ill-posed. In a changing geometry, energy is not always a number you can sum over the entire universe in a coordinate-independent way. The equations remain consistent, but the intuition built from isolated systems breaks. Cosmology forces us to distinguish local conservation laws from global accounting identities. The visuals can show a ledger that keeps balancing in each small patch, while the total at the bottom refuses to settle into a single invariant figure. Gravitational energy complicates the story further, because gravity is not just another field living on spacetime. In many heuristic treatments, gravitational potential energy is negative, and this sign matters for origin stories. As the universe expands, matter and radiation can have positive energy, while gravity contributes negative energy. In some models, the total can sum to 0, though defining that total precisely is gauge-dependent and subtle, and it depends on boundary conditions at infinity that a closed universe lacks. The narrator can stress the careful language, can, and in some treatments, are not evasions but honest qualifiers. This is not a license for sloppy claims, and the narration should emphasize restraint. It is a statement about what the equations allow, and about why the objection must be phrased carefully. A universe can expand and cool without a conserved global energy in the usual sense. Quantum creation scenarios exploit that looseness, but they still must satisfy the constraints of quantum gravity, not just rhetorical slogans. The documentary can let the phrase "from nothing" hang in the air, then quietly replace it with "from a quantum state with no classical spacetime." Now we return to the classical singularity theorems because they set the stakes. The Hawking-Penrose singularity theorems show that under certain conditions, spacetime geodesics are incomplete, meaning classical trajectories cannot be extended indefinitely into the past. Roughly, if gravity is attractive, certain energy conditions hold, and expansion is present, then a past boundary is unavoidable. In classical general relativity, the Big Bang singularity is not an artifact of perfect symmetry. It is generic under those assumptions. The theorems were a turning point historically because they made the singularity problem hard to dismiss as a mathematical curiosity. The theorems are powerful because they do not depend on the details of matter, only on broad conditions like the positivity of energy density and the focusing of geodesics. They tell us that classical spacetime, treated as a smooth manifold with a metric, cannot be extended past a certain point if those conditions are met, but they do not tell us what happens at that boundary. They point to the failure of the classical description, not to a specific replacement. In the visuals, geodesics can be drawn as converging lines that simply stop, as if the paper itself ends. But the theorems are conditional, and the conditions are precisely where early universe physics becomes exotic. They assume classical spacetime and certain energy conditions, like the strong energy condition, which roughly encodes that gravity focuses geodesics. Inflation already violates the strong energy condition because of its negative pressure, which changes how geodesics converge. Quantum fields can violate classical energy conditions in controlled ways, through effects like Casimir energy, and through constraints known as quantum inequalities. The narrator can underline the nuance. Violations are not arbitrary, because quantum theory limits how large and how long negative energy can be. So there are loopholes, and the documentary should treat them as openings rather than escapes. Quantum effects can modify the effective stress energy, changing the focusing behavior that drives the theorems. Higher curvature corrections can change the dynamics near the Planck regime, where the Einstein-Hilbert action may be only the first term in an expansion. The theorems then no longer force a classical singularity, though they still warn that something non-classical must occur. The theorems do not tell us what replaces the singularity. They tell us we cannot avoid new physics. The visuals can show the classical equations fading, then being overlaid by new terms that become dominant as curvature rises. Quantum cosmology is one candidate for that new physics, and it aims to replace a singular boundary with a quantum state and a boundary condition. It does not necessarily give a before, because it may dissolve the notion of before at the deepest level. It offers a different kind of origin story, one written in amplitudes rather than events. The beginning becomes a statement about allowed geometries and their weights, not a moment on a clock. The narrator can make the shift explicit. We are not rewinding a film, we're changing the rules of what counts as a frame. Yet the chapter must stay honest about what is unsettled, because the foundations are still under construction. The Wheeler-DeWitt equation is not derived from a complete quantum gravity theory in a universally accepted way, and different approaches motivate different forms. Factor ordering ambiguities and measure choices affect results, sometimes dramatically. Path integrals over geometries are mathematically treacherous, because the space of metrics is vast and the integral is not rigorously defined in the way it is for ordinary fields. Even the act of summing over all geometries hides a question: what counts as distinct and what is merely a relabeling? Even the contour choices in complexified metrics can change the answer, which is both a technical and conceptual warning. When we say imaginary time, we are choosing a particular analytic continuation, and not all continuations are equivalent. The saddle points we keep and the ones we discard can alter the predicted weighting of histories. These are not minor details, because in quantum cosmology the boundary condition is the theory's main input. The documentary can visualize this as alternative paths through a complex plane, each path selecting a different set of contributing geometries. Even the meaning of probability is contested, and the contest is unavoidable. In a closed universe, what does it mean to normalize the wave function, and what inner product should we use? What defines an ensemble when there is only one universe, and when observers are part of the system? Many proposals borrow intuition from laboratory quantum mechanics, but the translation is imperfect, and interpretation becomes entangled with calculation. The narrator can ask a pointed question. If probability is about frequencies, what does it mean when there is only one cosmic trial? Observational discrimination is also hard, and the difficulty is not just that the signals are faint. Inflation can erase many details of initial conditions, making different quantum origins converge on similar late-time universes. Cosmic variance limits our access to the larger scales where some signatures might live, because we only have one sky to measure. Foregrounds and systematics complicate the extraction of tiny deviations from the simplest spectra, and small anomalies can be statistical mirages. The documentary can show the CMB map with masked regions, reminding us that the data itself has blind spots. Still, the chapter insists on what could be testable, because the point is not to retreat into uncheckable speculation. Boundary conditions can influence the likelihood of long inflation, which affects the distribution of curvature and the amplitude of perturbations. Non-standard initial states can produce specific oscillatory features or suppressed power at low multipoles, patterns that can be searched for statistically. Primordial gravitational waves, if detected, would constrain the energy scale of inflation and could indirectly pressure quantum origin models, because the allowed potentials and histories would narrow. The narrator can frame it as a wager. Even if the beginning is hidden, it may have left constraints we cannot escape. The documentary's tone stays mysterious, but the content stays grounded, and that balance matters. These proposals are not metaphysical declarations about why there is something rather than nothing. They are attempts to compute a wave function and extract semi-classical predictions, even if the predictions are probabilistic and measure-dependent. Their nothing is a physical limit, not a philosophical void, and the distinction is the chapter's moral center. The visuals can return to the vacuum ocean, now paired with equations, restlessness given a precise form. Now we turn the hook one more time, because the language itself is part of the trap. If time is emergent, the phrase, "before the Big Bang," may not be a hidden chapter waiting to be revealed. It may be a category error that appears when we project everyday grammar onto quantum spacetime. The universe may not have begun in time. Time may have begun in the universe. the narrator can let the words slow, as if the sentence itself is testing whether it is allowed to have a before. But the story does not end in dissolution. If spacetime can be born from a quantum state, then spacetime might also avoid final boundaries, and the symmetry of that thought is hard to ignore. The same quantum corrections that soften a beginning could also soften an end, replacing a terminal singularity with a transition that opens the door to rebound and bounce scenarios, where contraction gives way to expansion. The visuals can hint at this with a curve that narrows, does not break, and then widens again. Continuity, where classical equations predicted a stop. This chapter ends by shifting the question from creation to continuation, which is a subtle but important change. If the beginning is a boundary condition, then other boundary conditions might describe a contraction turning into expansion without an infinite density point. A bounce would make before meaningful again, but in a different way, because before would refer to another semi-classical regime. The next chapter follows that possibility, where the universe's earliest chapter might be another universe's late chapter. The narrator can close the loop. The same tools we use to soften the beginning might also rewrite the ending. The central question remains the documentary's spine, and it is both scientific and existential without becoming metaphysical. Can Before the Big Bang make physical sense, and can any version be tested? Quantum cosmology offers a daring answer, and it does so with equations rather than proclamations. The beginning might be a quantum condition, not a first moment, and the clues might still be written across the sky. The Big Bang looks like a beginning only if the story starts there, with a sudden flare of heat and light. Chapter 4 weakened that assumption by making time and geometry quantum variables, not fixed stage props. Now we test a different escape route from the singularity. The hot Big Bang might be a transition from an earlier phase where before is not poetry but physics. Imagine the familiar cosmic timeline as a graph of size versus time, a curve we usually trace only to the right. In standard cosmology, we run that curve backward and it narrows toward a point until the mathematics breaks. Bounce cosmology starts with a simple reversal of the usual rewind, then refuses to stop at the breakdown. Expansion becomes contraction as we run the equations backward, then contraction reaches extreme density and turns around. The sequence is contraction, a high density phase, then expansion, with the Big Bang reinterpreted as a crossing. Visually, the bounce is a smooth valley rather than a cliff edge, a minimum scale factor that never hits zero. The Big Bang becomes the bounce surface, not an origin point, and the word initial becomes a statement about a phase transition. That change sounds semantic until you remember what singularities do, because a singularity is not just a large number, it is the loss of predictability. In practical terms, it is where the equations stop giving unique answers, even when you specify the state precisely. This idea is older than modern data, yet it keeps returning because the singularity keeps returning. Classical general relativity drives many contracting universes toward a crunch singularity, where curvature scalars diverge and geodesics end. The theorems of Hawking and Penrose made that logic hard to evade under ordinary energy conditions, and they did it with almost brutal generality. Quantum gravity candidates often try to replace that crunch with a finite, non-singular bridge. If the bridge exists, the word before regains physical meaning, because evolution continues through the dangerous region. A bounce is not automatically a cycle, and a cycle is not automatically stable, which is where the story becomes technical. A single bounce could connect one prehistory to our expansion without repeating, like a one-time reversal in a long trajectory. A cyclic universe repeats expansion and contraction, possibly forever, and then every imperfection has many chances to grow. The distinction matters because repetition amplifies every small problem, including entropy, anisotropy, and quantum instability. The first classical cyclic pictures were mechanical and intuitive, drawn when cosmology still borrowed metaphors from clockwork. The universe expands, slows, turns around, then collapses, then repeats, like a breathing sphere in a dark void. In those early models, matter and radiation dominate the dynamics, and curvature helps trigger recollapse when the density falls. The appeal is philosophical as much as physical, because it dissolves the need for a first moment. There is no first page, only an endless sequence of chapters, each one echoing the last. Yet classical cycles collide with thermodynamics, and the collision is not gentle. Entropy tends to increase, and each cycle produces more disorder than the last through irreversible processes. Even if the geometry repeats, the microscopic bookkeeping does not, because friction, particle production, and gravitational clumping do not run backward. That growth makes later cycles larger and longer, which is the Tolman problem. If cycles stretch without bound, the past cannot be an infinite repetition of similar eras. Tolman's argument is not a minor footnote, because it ties the arrow of time to the viability of an eternal past. Entropy is not just messiness in a casual sense. It is a count of how many microscopic arrangements fit the same macroscopic appearance. If entropy accumulates, then earlier cycles must have been smaller and shorter, with less room for complexity. Run the logic far enough, and the sequence still points toward a beginning, even if no cycle has a sharp starting line. The universe may refuse to begin, yet thermodynamics keeps asking where the low entropy came from. Modern cyclic models respond by changing what contraction looks like, because the naive collapse is a recipe for chaos. They do not rely on a matter-dominated contraction that becomes clumpy, turbulent, and anisotropic as density rises. Instead, they aim for a special contraction that smooths and flattens instead of shredding, acting like a cosmic ironing process. The key tool is the equation of state, which controls how different components scale as the universe shrinks. In the background equations, it decides which energy component outruns the others as the scale factor falls. In cosmology, pressure and energy density are linked by W, where P equals W times Rho, and that single parameter shapes the fate of perturbations. Ordinary matter has W near zero, and radiation has W equal 1/3, so both dilute in familiar ways. Vacuum-like energy has W near -1 and drives accelerated expansion, which is why it is central to inflation. Ekpyrotic contraction uses the opposite extreme, pushing W to very large values. That choice is not aesthetic. It is a lever that changes the hierarchy of terms in the Friedmann and Shear equations. Ekpyrotic models propose a slow contraction with a very stiff equation of state, with W much greater than 1. In that regime, anisotropies and curvature are diluted relative to the dominant component, because their energy densities grow more slowly than the stiff fields. The universe becomes smoother as it contracts, which is counterintuitive but calculable from the Friedmann and Shear evolution equations. Contraction becomes a cleaning phase rather than a prelude to chaos, at least in the idealized homogeneous picture. The remarkable claim is that the dangerous approach to high density can be dynamically tamed, not merely assumed away. To make that vivid, picture a contracting space where small directional distortions try to grow like wrinkles in fabric. In a generic collapse, those wrinkles dominate, and the approach to the crunch becomes the BKL mixmaster dance. In an ekpyrotic collapse, the stiff component overwhelms the wrinkles, pressing them down as the scale factor falls. The contraction can be slow in time while still being powerful in its smoothing effect, a subtle but crucial point. On screen, the chaos of a generic collapse becomes a quiet narrowing, as if the universe is deliberately choosing order. The word ekpyrotic comes from an ancient idea of cosmic renewal, but the modern version is technical and tightly parameterized. It often uses a scalar field rolling down a steep negative potential, where the field's kinetic energy and potential energy conspire to produce W far above 1. The energy density grows during contraction, yet the field stiffness suppresses mixmaster-like anisotropic instabilities that would otherwise dominate. The goal is to reach a bounce with controlled initial conditions, not a chaotic end state. The steepness of the potential matters because it sets how quickly the field rolls, and therefore how stiff the effective fluid becomes. Scalar fields are not exotic in cosmology, because inflation already depends on them in many constructions. What changes here is the sign and steepness of the potential, and the requirement that the field remain stable against perturbations. A steep negative potential can invite instabilities if not handled carefully, so model builders often add additional structure. The ekpyrotic phase is therefore both elegant and delicate, a balance between smoothing power and theoretical control. The same mathematics that suppresses anisotropy can, if mishandled, amplify unwanted fluctuations. Some cyclic versions embed this in string-inspired brain pictures, where the geometry of extra dimensions becomes part of the narrative. Our visible universe is a three-dimensional brain in a higher dimensional bulk, with fields confined to the brain like vibrations on a membrane. A collision between brains can deposit energy and create a hot expanding phase, producing matter and radiation as the brains interact. In that story, the Big Bang is a brain interaction, not a space-time singularity. The bounce is reimagined as a microphysical event, with a calculable channel for reheating. For visuals, the brain picture invites a slow, tense approach. Two vast sheets drifting through a higher dimensional darkness. Their separation shrinks with almost imperceptible patience, while faint ripples, fields and fluctuations shiver across their surfaces. At the moment of encounter, energy flashes into familiar particles, and the brain that carries our physics heats like a struck drumhead. The imagery is dramatic, yet the scientific claim is specific. It is a mechanism for turning contraction into a hot start without requiring infinite curvature. The brain language is a model-building scaffold, not an observed fact, and the documentary should keep that distinction crisp. It offers a way to interpret the bounce as a collision event with microphysical degrees of freedom, which helps when we ask where the heat comes from. It also provides new knobs for entropy and reheating, because energy can flow into sectors beyond our brain. Still, the core claim is simpler than the imagery. The hot beginning is a transfer of energy across a transition. Ekpyrotic models must also generate the right primordial perturbations, because smoothness alone is not enough. Inflation stretches quantum fluctuations during accelerated expansion, turning microscopic uncertainty into macroscopic structure. Ekpyrosis must create fluctuations during contraction and carry them through the bounce, while keeping them nearly scale invariant. The mechanism often uses multiple fields, where entropy perturbations convert into curvature perturbations. The details decide whether the result matches the CMB or fails in a way the sky can see. A model can be perfectly non-singular and still be observationally wrong. The central observational target remains the same because the universe has already handed us a statistical blueprint. We need nearly scale invariant, nearly Gaussian, mostly adiabatic curvature perturbations, with the right phase coherence to seed acoustic peaks. We need the peak structure to come out right after evolution, through recombination and later cosmic history. Any bounce scenario must reproduce the same pattern inflation fits so efficiently. The bounce is not judged by elegance, but by the sky, by the cold, precise arithmetic of angular power spectra. Now we shift to a different modern approach, loop quantum cosmology, which begins from a different instinct. LQC starts with loop quantum gravity ideas applied to a homogeneous universe, taking quantization seriously at the level of geometry itself. The claim is not that spacetime is a smooth continuum at arbitrarily small scales, like a perfect fluid. Geometry becomes quantized, with discrete spectra for areas and volumes, so small has a minimum meaningful scale. At Planckian densities, those quantum geometry effects modify the Friedmann equations, changing how expansion responds to energy. In the effective description, the classical relation between density and curvature is corrected by terms that become dominant only near the critical density. In LQC, the modification acts like a repulsive term at extreme density, though it is better described as a correction to the gravitational response. Gravity remains attractive at ordinary densities, so galaxies and clusters still form in the usual way. But near the Planck scale, when density approaches a critical value, the effective dynamics change sign. The classical singularity is replaced by a bounce at a finite maximum density. The universe contracts, reaches that density, then expands, with the bounce occurring when the Hubble parameter crosses through zero. This repulsion is not a new force added by hand, which is part of LQC's appeal to many theorists. It comes from how quantum geometry changes the relation between curvature and energy density, effectively encoding holonomy corrections in the equations. The effective equations show a correction that flips the sign of the Hubble rate's derivative near the critical density, making contraction slow and then reverse. The bounce is a dynamical consequence of the quantization scheme. It is also a promise that singularities are artifacts of treating geometry as continuous. To ground this, it helps to picture curvature not as infinitely divisible bending, but as built from discrete quanta that resist being packed beyond a limit. In the same way that matter has quantum pressure in a white dwarf, geometry in LQC has a kind of quantum stiffness. That analogy is imperfect, yet it captures the intuition. The crunch is avoided not by magic, but by new microscopic rules. The universe does not hit an edge, it hits a regime change. In that regime, familiar spacetime becomes an emergent approximation, like smooth water emerging from molecules. LQC is conceptually clean in one sense, because it gives a concrete mechanism for non-singular evolution within a specific quantization framework. It also raises hard questions about what survives the bounce, and whether the effective description remains reliable for all relevant modes. If the bounce is deterministic in the effective theory, then pre-bounce data maps to post-bounce data, like a transfer function. That mapping becomes a potential source of observable memory, and also a point where assumptions about the quantum state matter. Even the choice of what vacuum means in a contracting universe can shift predictions, which is unsettling and scientifically useful. Other non-singular bounce ideas exist beyond ekprosis and LQC, and they illustrate how many ways theorists try to tame the same divergence. Some use modified gravity terms, like higher curvature corrections that dominate at high density, echoing the idea that Einstein's action is only the first term in an expansion. Some use matter that violates certain energy conditions in controlled ways, because a bounce in classical relativity often needs such violations. Some use ghost condensates or Galilean-like fields to achieve a stable bounce without catastrophic instabilities, carefully arranging higher derivative terms. Each approach must fight the same enemies: instability, anisotropy growth, and loss of predictivity. A bounce is only useful if it is stable and calculable, which is a stricter demand than simply avoiding infinity. In a contracting universe, anisotropies typically grow faster than ordinary matter, because shear scales aggressively as the scale factor shrinks. That growth can drive a chaotic approach to a crunch, known from BKL behavior, where different directions expand and contract in rapid sequence. Ekpyrosis tries to suppress that growth with W much greater than 1, turning the stiff component into a stabilizing background. LQC tries to bypass the crunch with quantum corrections that cap density. Every model must show it avoids a generic collapse into disorder, because the generic outcome is not a smooth bounce, it is a messy end. Now the thermodynamic problem returns in a sharper form, because cycles are not just geometry repeating, they are matter processes repeating. Each hot phase produces entropy through particle interactions, structure formation, and black hole growth, and those processes are not reversible. Stars burn fuel, galaxies merge, and gravitational collapse hides information behind horizons, all of which push entropy upward. If that entropy accumulates, cycles cannot be identical, even if the scale factor repeats qualitatively. The universe would drift, and the past would not be an infinite repetition of the present. The Tolman problem forces modern cyclic models to propose a resolution, and each resolution has a cost. One idea is entropy dilution, where each cycle expands so much that entropy density resets, making the next cycle effectively fresh within any fixed comoving patch. Another idea is that entropy is dumped into extra dimensions or hidden sectors, leaving our observable region effectively refreshed. Another approach redefines what a cycle is, treating the repeating variable as geometry, while matter content changes. None of these are free. Each adds assumptions that must be consistent with known physics. Entropy dilution sounds like a trick, yet it is a real dynamical possibility if the expansion factor grows dramatically from cycle to cycle. If the scale factor grows by a huge factor, then entropy per comoving volume can become negligible, even if total entropy increases. But that growth implies cycles are not truly periodic in the usual sense, because the same cycle never returns at the same scale. The universe becomes cyclic in shape, not in scale, like a melody repeated in ever higher keys. The past can be infinite, yet the cycles stretch and drift. Dumping entropy into extra degrees of freedom is also plausible in principle, especially in brain-inspired pictures where the bulk is a reservoir. If the bounce involves sectors we do not observe, they can act as entropy sinks, absorbing heat and disorder that would otherwise accumulate. But then the model must explain why those sectors do not leave other traces, such as extra radiation or fifth force effects. It must also explain why the coupling is strong enough to remove entropy, yet weak enough to keep our late universe standard. The solution becomes a balancing act, one that can be tested indirectly by constraints on extra relativistic species. There is also a deeper question about what counts as entropy in quantum gravity, because gravity blurs the boundary between matter and geometry. If space-time microstates are discrete, then gravitational entropy may not behave like a simple fluid variable that you can track with a single number. Black hole entropy suggests gravity stores information in horizons and geometry, and that storage is enormous compared to ordinary matter entropy. A cyclic model must say what happens to horizons across a bounce. Does information disappear, scramble, or re-emerge, and in what form? And if it re-emerges, is it recognizable, or only present as a faint statistical bias? This leads to the chapter's suspense, because before becomes meaningful only if it can leave a trace. If there was a before, could it leave scars we can still search for, or would the bounce erase everything like a cosmic fire? A bounce is a filter that can erase, distort, or transmit information, depending on how smooth and how adiabatic the transition is. The key is perturbations, because perturbations are what we can observe. We cannot observe the background scale factor before the bounce directly. We can observe statistical patterns imprinted on the CMB and large-scale structure. Perturbations in bounce cosmology have two tasks, and failing either one breaks the model's link to reality. They must be generated with the right spectrum during contraction, or near the bounce, which is already a non-trivial constraint. They must pass through the high-density phase without being destroyed or turned into the wrong kind of mode, because the bounce can mix variables. In general relativity, matching conditions across a singular surface are ambiguous, and different prescriptions can yield different outcomes. In a non-singular bounce, the evolution can be continuous, but it can still mix modes in ways that matter observationally. The bounce is not merely a background event, it is a scattering problem for fluctuations. In inflation, the curvature perturbation on superhorizon scales is conserved under broad conditions, which is why the theory is so predictive, that conservation makes inflation robust against many microphysical details, because once modes exit the horizon, they freeze in a controlled way. In a bounce, the contracting phase can amplify different variables, and the conserved quantity can differ from the inflationary case. The bounce can convert growing modes into decaying modes, or the reverse. Small theoretical choices can become large observational differences, which is both an opportunity and a danger. The same flexibility that allows a bounce can also make it fragile. Ekpyrotic models often generate nearly scale-invariant perturbations through an entropic mechanism, which is a clever detour around a basic obstacle. A second field produces entropy perturbations with the desired spectrum during slow contraction, while the curvature perturbation remains small and controlled. Later, a conversion process turns those entropy perturbations into curvature perturbations, often during a bending of the trajectory in field space. That conversion can produce non-Gaussianity, often of the local type, because nonlinear interactions become important. The non-Gaussian signal becomes a key discriminator, almost a fingerprint of the conversion step. It is also a reminder that the early universe may have been multi-component, with hidden directions in field space shaping visible structure. LQC often starts with vacuum fluctuations in the contracting branch, treating the pre-bounce universe as a quantum state evolving under modified dynamics. Quantum geometry corrections then evolve those fluctuations through the bounce, and the details can depend on the chosen initial state and the treatment of transplanckian modes. Depending on initial state choices, LQC can predict power suppression or oscillations on the larger scales, where the bounce scale imprints a characteristic feature. Those features are subtle because cosmic variance is large at low multipoles, limiting how sharply we can test them. Still, they offer a concrete place to look for pre-bounce memory, like a faint echo that survives the crossing. Now we connect these mechanisms to the data language introduced earlier, because the sky speaks in parameters and correlations. The power spectrum tilt, its running, and higher order correlations are the main handles, along with constraints on isocurvature modes. Inflation predicts a near-scale invariant spectrum with a small red tilt and small running in simple models, which matches current measurements well. Many bounce models can match the tilt, but they often predict different running behavior because the background evolution differs. They can also predict distinctive shapes of the bispectrum, which encode how modes interacted when they were born. If the early universe had a bounce clock, its rhythm may be encoded in these correlations. Non-Gaussianity is especially diagnostic because it is hard to hide once it is large, and it is difficult to mimic accidentally. Local non-Gaussianity can be large in some ekpyrotic conversions, because the conversion from entropy to curvature can be strongly nonlinear. Equilateral or folded shapes can appear in models with non-trivial kinetic terms near the bounce, where higher derivative operators become important. Current limits already exclude some parameter ranges, turning parts of the bounce landscape into fossils. Future surveys could tighten constraints enough to make the bounce story either compelling or cornered. The question is not whether a bounce is imaginable, but whether it is statistically compatible with the sky we actually see. Tensor modes are another dividing line because they respond differently to contraction than to inflationary expansion. Inflation generically produces a primordial gravitational wave background with a nearly scale-invariant tensor spectrum, and its amplitude is tied to the energy scale of inflation. Many ekpyrotic scenarios predict a blue tensor spectrum with very small amplitude on CMB scales, because the mechanism that smooths the universe does not efficiently amplify long wavelength tensors. LQC can modify tensor evolution near the bounce, potentially producing features or suppressions depending on the effective corrections. The tensor-to-scalar ratio remains a central judge, because it compresses a great deal of physics into one observable number. Large-scale CMB anomalies enter as a tempting but dangerous clue, because humans are pattern-seeking and the data are limited. Some maps show low power at the largest angular scales and hints of hemispherical asymmetry, along with other alignments that may or may not be meaningful. These could be statistical flukes, foreground artifacts, or late-time effects tied to our local environment. Bounce models sometimes claim they can explain such anomalies through pre-bounce initial conditions or bounce-induced features that affect the lowest multipoles. The narration must keep the tension. The anomalies are suggestive, but not decisive. Now we bring in gravitational waves as messengers across the bounce, because they are among the cleanest carriers of early universe information. Gravitational waves interact weakly, so they can travel largely unscathed from very early times, even when matter was a dense plasma. A bounce could generate a stochastic background with a spectrum different from inflation's, especially if the dynamics near the bounce are violent or involve stiff components. The key is frequency, because different detectors listen to different bands. A signal can be invisible to the CMB yet loud at higher frequencies, which changes how we design tests. In that sense, gravitational waves are not one experiment but a whole spectrum of experiments. CMB modes probe extremely low-frequency gravitational waves, corresponding to horizon scales at recombination, and they are limited by foreground dust and lensing. Pulsar timing arrays probe nanohertz frequencies, sensitive to waves with periods of years, by looking for correlated timing shifts across the sky. Space interferometers like LISA probe millihertz bands, where compact binaries and possible primordial signals can overlap. Ground-based detectors probe tens to thousands of hertz, where astrophysical mergers dominate but a blue primordial background could rise. A bounce background could peak in one band and be absent in another. The search must be multi-instrument, and the interpretation must be cautious. Inflationary tensors, if nearly scale invariant, spread power broadly across frequencies with a gentle tilt, though reheating details can add features. Bounce-generated tensors can be blue, rising strongly with frequency, because a stiff equation of state changes how tensor modes evolve relative to the horizon. That makes CMB constraints weak while interferometer constraints become important, flipping the usual hierarchy of tests. It also means a detection in one band could rule out simple inflationary expectations, even if the CMB remains quiet. Gravitational wave astronomy becomes a test of cosmic prehistory, not just a catalogue of astrophysical events. But gravitational wave backgrounds are not clean by default, and a documentary should show the discipline behind the excitement. Astrophysical sources create their own stochastic signals, from merging black holes and neutron stars to unresolved populations of binaries. Some speculative sources, like cosmic strings, can also produce backgrounds with distinctive spectra, complicating attribution. Separating primordial from astrophysical backgrounds requires spectral shape, anisotropy, polarization information, and cross-correlation tests across detectors. The messenger is powerful, but the decoding is hard, and false positives are part of the landscape. Now we return to the philosophical tension, because bounce cosmology changes what origin means without dissolving the deepest questions. If time extends indefinitely through cycles, the demand for a first cause can feel less urgent, because there is no first tick. The universe does not start, it persists, and persistence can sound like an answer. Yet the question can reappear in a different form, sharper, because it targets laws rather than events. Why do the laws allow a bounce, and why do they select the conditions that make cycles possible? An eternal past also pressures the arrow of time, because cycles invite symmetry, while experience insists on direction. If cycles repeat, why does entropy increase in the direction we call future, rather than oscillating or resetting cleanly? Some cyclic proposals claim the arrow resets at each bounce, or that observers always find themselves in entropy-increasing branches, because only those branches support complex structures. Others argue the arrow is global, and cycles are not symmetric, with each bounce inheriting a thermodynamic gradient. The arrow becomes a diagnostic of whether a model is coherent. A universe that refused to begin still must explain why it remembers a direction. The central question of the series sharpens here, because the idea of before the Big Bang is no longer metaphysical by default. Can the idea of before the Big Bang make physical sense, and can it be tested with the tools of observation? Bounce models answer yes in a literal way, because they provide a prior semi-classical phase where time and causality still operate. They also answer yes in a statistical way, because they predict distinctive perturbation patterns that can be compared with data. But they pay for that clarity with new demands. They must control contraction, entropy, and mode evolution, all without breaking known physics. Now we tie back to inflation without turning this into a rerun, because the comparison is the pressure test. Inflation is a prologue that can erase initial conditions, which makes it hard to see earlier chapters even if they existed. Bounce models invert that logic, using contraction to smooth the universe and, in some channels, preserve memory. They try to generate the same smoothness and flatness through contraction, not expansion, and they aim to keep memory rather than erase it. The inversion is conceptually beautiful, but it shifts the technical burden. It also changes the emotional texture of the origin story, from a burst that wipes the slate clean to a crossing that might remember. The comparison is not only about which story is prettier, because beauty is not a measurement. It is about which story is more robust under small changes, because the early universe is not obliged to be fine-tuned. Inflation has attractor behavior in many models, and it has a simple perturbation mechanism that has survived decades of scrutiny. Bounce models can be elegant, but they often depend on avoiding instabilities and tuning conversion processes, especially when multiple fields are involved. The sky will decide, but the theory must first survive its own internal stresses. We now push the suspense toward observation, because this is where the universe can answer without speaking. If a bounce occurred, it might leave a cutoff or oscillations in the scalar power spectrum at the larger scales, where modes were sensitive to the bounce scale. It might leave specific non-Gaussian shapes tied to conversion physics, acting like a signature rather than a generic prediction. It might leave a tensor spectrum that rises with frequency and becomes detectable by future interferometers, even if CMB tensors remain undetectable. It might also leave subtle phase correlations that standard inflation does not favor, though those are harder to extract. The question becomes almost forensic. What would a prehistory look like after it has been filtered through a bounce? Yet the universe is not obligated to leave readable scars, and that uncertainty is part of the mystery. A bounce could be so violent that it thermalizes and erases detailed information, leaving only a hot, nearly featureless restart. It could be so smooth that it transmits only coarse statistical properties, like the tilt but not the phases. It could scramble phases while preserving the power spectrum, making the memory hard to extract with any realistic survey. The narration should hold that uncertainty as a scientific tension, not a rhetorical trick. The absence of scars would still teach us about the bounce's nature. Now we widen the frame to cycles again, because cycles raise a final structural question about what repetition even means. If the universe cycles, does it cycle in time, or in something more abstract that does not correspond to a simple clock? Some proposals suggest that what repeats is not a timeline but a geometric transformation, where the physics is mapped from one regime to another. One universe can become the next through a conformal rescaling, where the end of one era maps to the beginning of another with a change of units. The bounce becomes a change of description rather than a collision of phases, and the stitching becomes the central act. This is the transition we need for the next chapter's escalation, because it points beyond the usual bounce diagram. Some models go further than bounces and cycles in time, proposing cycles in geometry, where the universe's remote future becomes another universe's remote past. The Big Bang becomes a matching surface between aeons, not a rebound from contraction, and the word before becomes a statement about mapping. The question of before becomes a question of how spacetime is stitched, and what information can cross the seam. If the seam is real, it is not a wall, it is a rule. and rules can sometimes be tested. So Chapter 5 ends with the disciplined promise, because the scientific posture is not certainty, but testability. If there was a before, it might have left statistical fingerprints in light and gravity, faint but structured. If there was no before, the failure to find those fingerprints still constrains what quantum spacetime can be, narrowing the space of viable theories. Either way, the beginning becomes less a boundary of language and more a target for measurement, shaped by spectra, correlations, and careful inference. The universe refused to begin, and that refusal might be written in the faintest patterns we can still read. We have chased before into bounces and quantum boundary conditions, and the trail keeps bending in ways that resist ordinary storytelling. Chapter 6 pushes further, because some ideas claim the Big Bang is not an origin at all. They claim it is a translation between descriptions, or a seam stitched between cosmic eras. The central question stays fixed, even as the mathematics grows stranger. Can "before the Big Bang" make physical sense, and can any version be measured with real instruments? The hook also stays sharp because the universe keeps leaving fossils in its oldest light. If time began at the Big Bang, why does the cosmos still whisper about earlier structure, about patterns that look prepared? Now we take a guided descent into possibilities that feel impossible, yet follow mathematical pressure. Each step loosens a familiar intuition, then replaces it with an invariant that survives when scale and locality dissolve. The story becomes less about events, and more about what remains meaningful when our usual clocks and rulers fail. In that regime, beginning can become a coordinate choice rather than a physical fact. First, we enter conformal cyclic cosmology, proposed most famously by Roger Penrose, whose work on singularities and black holes helped define modern relativity. CCC does not start with contraction and a bounce, and it does not require a universe that turns around. It starts with expansion that never ends, then asks what an end of time really means when matter thins away. In Penrose's framing, the deep question is not whether the universe ends, but whether the end can be redescribed as another start. In standard cosmology, the far future is cold and dilute, with galaxies isolated beyond horizons as space expands faster than light can bridge. Stars burn out, white dwarfs cool, and the remaining gas becomes so thin that collisions are rare. The universe approaches emptiness in a practical sense, even if quantum fields never vanish. CCC adds a crucial condition that changes what emptiness means physically. If rest mass effectively disappears, then absolute scale stops mattering, because there is no stable, massive object left to define a preferred unit. The key physical ingredients are extreme, but they are not obviously forbidden by known laws. Protons might decay through grand unified processes, though experiments only set lower limits on their lifetime. Those limits are already enormous, which is why this remains a hypothesis rather than a prediction. Yet CCC does not require a specific decay channel, only a future where stable mass becomes irrelevant. Even if protons survive, black holes do not, and that fact is on firmer theoretical footing. Hawking radiation makes black holes evaporate because quantum fields near the horizon allow energy to leak outward as thermal emission. For stellar mass black holes, the timescales are absurdly long, far beyond the current age of the universe. For supermassive black holes, the timescales are longer still, stretching into numbers that feel more like symbols than durations. Yet the direction is clear in the equations. Given enough time, horizons shrink and vanish. When the last black hole evaporates, the dominant remaining content is low-energy radiation, and any fields that behave as effectively massless. CCC leans on a specific asymptotic picture, and it is worth seeing it as a visual sequence rather than a single claim. In the far future, after black holes evaporate, the universe is dominated by radiation and massless or effectively massless fields. Photons and other light-like quanta stream through a space that has become almost perfectly transparent. With no stable massive particles, there is no preferred ruler, because rulers are made of mass bound into structures. The physics becomes scale-free in the relevant sense, even though the universe can still be expanding. This is where the word conformal enters, and it must be made accessible without losing precision. A conformal transformation rescales the metric by a smooth factor that can vary across spacetime, changing measured distances while preserving angles. In plain terms, it is like stretching a map so that local shapes keep their orientation, even as the overall scale changes. Light cones keep their shape, which means the causal ordering of events stays intact. If you care about what can influence what, conformal structure preserves the essential skeleton. Conformal structure is the causal backbone of spacetime, and in relativity it is more fundamental than it first appears. It tells which directions are light-like, time-like, and space-like, and that classification governs signals and horizons. If only massless particles remain, their motion is tied to that light-like structure, not to any absolute scale. Massive particles care about proper time and rest mass, but massless particles do not carry a rest frame. In a world made only of radiation, the universe can lose its operational meaning of size. CCC claims a startling equivalence that sounds like poetry until you see the geometric move. The infinitely expanded, empty future of one cosmic era can be conformally mapped to a new Big Bang. Penrose calls each era an aeon, a word chosen to emphasize both continuity and separation. The end of one aeon becomes the beginning of the next, after a rescaling that compresses an infinite future into a finite boundary. In that picture, the Big Bang is not a first moment, but a matching surface. This is not a bounce in time that turns contraction into expansion, and that distinction matters for what the theory is actually doing. It is a matching of conformal geometries, where the metric is rescaled so that an infinite future becomes a finite boundary. The Big Bang becomes a conformal boundary surface, not a singular origin where physics breaks. The singularity is softened by changing what counts as physically meaningful. CC is not saying the universe avoids extremes, but that the extremes can be redescribed without a blow-up in the conformal frame. The narrative tension is immediate because it flips the emotional direction of cosmology. If the Big Bang is a conformal redescription of a remote future, then before becomes after in an unexpected sense. The thing we call the beginning could be the far future of another universe, seen through a change of scale. The question becomes whether our earliest light contains any trace of that previous era. If it does, the sky is not only a record of our history, but a palimpsest. But CCC must also confront the arrow of time, because cycles invite symmetry while experience insists on direction. Penrose argues the arrow is tied to gravitational entropy, which behaves differently from ordinary thermal entropy. Early universes are smooth, with low Weyl curvature, while late universes are clumpy and black hole rich. The Weyl curvature is a measure of tidal distortion, and it grows as structure forms. In this view, the early universe is special not because it is hot, but because it is geometrically simple. CCC proposes a reset mechanism, and it is both elegant and controversial. Black holes dominate gravitational entropy because their horizons encode enormous entropy in the Bekenstein-Hawking sense. Their evaporation removes the main repositories of that entropy, at least in the form that gravitational clumping represents. If the far future contains only radiation, the Weyl curvature can effectively fade in the conformal picture. The next aeon can begin smooth again, because the conformal boundary suppresses the memory of scale-dependent clumping. This is a bold claim, and it is also where CCC becomes vulnerable to both physics and philosophy. It depends on what counts as mass in the far future, and on how fields behave when the universe is extremely dilute. It also depends on how to treat the cosmological constant, which sets an asymptotic de Sitter-like expansion with horizons. De Sitter horizons carry their own entropy, which complicates any simple narrative about entropy being removed. CCC must thread a narrow path between geometric elegance and thermodynamic realism. There is also a subtle technical tension hiding behind the words effectively massless. In the standard model, particles acquire mass through mechanisms like the Higgs field, and mass is not merely a label. If the Higgs vacuum expectation value remains, then many particles remain massive in principle, even if no stable massive composites survive. CCC often emphasizes the disappearance of rest mass as an operational concept, not necessarily a literal vanishing of mass parameters. That distinction matters, because operational meaning is not the same as fundamental ontology. The theory asks us to accept that what cannot be measured may not be physically relevant. Now we ask the only question that matters for a documentary anchored in physics. If CCC is real, what could it leave in the sky that is not merely interpretive? CCC's promise is not merely philosophical continuity or a comforting loop. It is that violent events in a previous aeon could imprint patterns on our cosmic microwave background. The CMB is our oldest photograph, taken when the universe became transparent about 380,000 years after the hot beginning. If anything crosses aeons, the CMB is where we would look. The most discussed proposed signature is a set of low-variance circles in the CMB, and the claim is easy to visualize. Imagine the last scattering surface as a sphere around us, a shell of ancient light. Now imagine a burst of gravitational radiation from a previous aeon crossing the conformal boundary and propagating into ours. Where that burst intersects our last scattering sphere, it would trace a circle. CCC suggests that inside such circles, temperature fluctuations might show unusually low variance, as if some process smoothed them. The motivating events are dramatic because the previous aeon has had an effectively infinite time to build enormous black holes. Energetic events like supermassive black hole mergers would send out bursts of gravitational radiation. In general relativity, gravitational waves carry energy and distort spacetime itself, and in CCC they become candidates for cross-eon messengers. Those bursts could intersect our last scattering surface as circles, not because circles are mystical, but because spheres intersect spheres in circles. Geometry makes the prediction plausible in form, even if not in magnitude. In CCC, the mapping between aeons can carry certain information across the conformal boundary, but it's not a memory of details. The claim is not that galaxies, stars, or specific structures survive intact, because the conformal mapping crushes scale. The claim is that some large-scale coherent features could pass through as subtle, statistical anomalies. The surviving information would be more like a fingerprint than a photograph. That is why the proposed signatures tend to be statistical rather than deterministic. But the contested status must be stated clearly, because the CMB is a noisy courtroom with limited evidence. Searches for low-variance circles have produced claims and counterclaims with disagreements about statistics, look-elsewhere effects, and foreground handling. The CMB has limited independent modes on large scales, and cosmic variance is unforgiving. Even perfect instruments cannot beat the fact that we observe only one universe. When the sample size is one sky, the line between pattern and coincidence becomes thin. Even defining what counts as significant is hard, because significance depends on how many tests you effectively performed. If you search many circle radii and many centers, you will find patterns by chance, even in random Gaussian skies. Robust inference requires careful null tests, simulations with the same noise and masking, and pre-registered criteria that limit after-the-fact tuning. Foregrounds from our galaxy must be removed, and masking can create spurious structures. CCC's observational case remains unsettled, and that uncertainty is part of the story. CCC also suggests other possible imprints, including Hawking points, localized hotspots associated with the final evaporation of supermassive black holes in the previous aeon. The idea is that the last stages of evaporation could release energy in a way that maps through the conformal boundary. These too are debated, and the statistical arguments are delicate. The documentary must keep the mystery without overselling certainty, because the difference between a hint and a discovery is methodological discipline. What would it mean, emotionally and scientifically, if a tiny hotspot carried a message from a universe before ours? If CCC feels like a cosmic loop, it is also a lesson in what we mean by same. Each aeon is not a replay, and CCC does not promise recurrence of specific histories. It promises a kind of continuity of causal structure, not continuity of content. That distinction is easy to miss in casual summaries, yet it is central to the proposal's scientific character. CCC is not mythic repetition, but a geometric identification of boundaries. The question is whether nature uses that identification, or whether it is a beautiful mapping with no physical counterpart. Now we widen the frame, because CCC is only one way to dissolve the beginning without invoking a literal prior time. Another route says the universe's deepest description may not even live in our number of dimensions. It says gravity and spacetime might be emergent, like a projection from a more fundamental theory. In that view, asking what happened before may be like asking what is north of the North Pole. The question might be ill-posed in the wrong language, even if a deeper language exists. This is where the holographic principle enters, and it begins with black holes, the same objects that CCC uses as entropy engines. In the 1970s, Jacob Bekenstein argued that black holes should have entropy, because otherwise the second law of thermodynamics could be violated. Stephen Hawking then showed that black holes emit radiation with a temperature, making the thermodynamic analogy concrete. The resulting entropy formula is proportional to the horizon area, not the volume. That scaling is a shock, because ordinary systems scale with volume as if every cubic centimetre holds independent degrees of freedom. The area law hints that information in a region might be bounded by its boundary, which is a radical constraint on what inside can mean. If true, the universe does not store degrees of freedom the way our intuition expects. The fundamental bookkeeping could be written on surfaces, with bulk physics emerging as an effective description. In plain language, the world might be like a three-dimensional image encoded on a two-dimensional screen. The metaphor is imperfect, but the constraint is precise. Too much information in a volume would collapse into a black hole. Holography is not only a metaphor, and that is why it has become one of the most important conceptual tools in quantum gravity. In certain spacetimes, it becomes a concrete duality with mathematical teeth. The best-known example is ADS-CFT, where a gravity theory in a higher dimensional anti-de Sitter bulk is equivalent to a conformal field theory on its boundary. This idea grew from string theory, but its impact has spread far beyond string-specific questions. It provides a working example of spacetime emerging from non-gravitational degrees of freedom. ADS-CFT gives a precise meaning to equivalent, and the precision is what makes it more than philosophy. Observables, correlation functions, and dynamics can be mapped between the two descriptions. Strong coupling in one picture can become weak coupling in the other, turning unsolved problems into solvable ones. It is a dictionary, not a vague analogy, and it forces consistency across the mapping. When the dictionary works, it means two very different-looking theories are the same physics in different languages. Our universe is not anti-de Sitter, and that limitation must be explicit because it shapes what we can safely claim. We appear closer to de Sitter on large scales because of dark energy, and de Sitter space has cosmological horizons that complicate boundary definitions. Still, ADS-CFT proves the core claim in at least one controlled setting. A gravity universe can be fully described by a non-gravitational theory in fewer dimensions. Once that is true anywhere, it becomes reasonable to ask where else it might be true. Now we connect holography back to the central question, because its relevance is not aesthetic but structural. If the early universe can be described holographically, then the Big Bang might not be a first moment in the fundamental theory. It might be a regime where the bulk spacetime description breaks down, while the boundary description remains well defined. In that case, before the Big Bang could mean before the bulk spacetime emerged, not earlier in time. The deeper theory might have a parameter that plays the role of time, or it might not. In cosmological holography, the goal is to find a dual description for expanding universes, and this is still an active frontier. Some approaches explore DS-CFT-like ideas, though they are less established than ADS-CFT and face technical obstacles. Others use holographic models of inflation, where primordial fluctuations are computed from a lower dimensional field theory. The hope is that the near-scale invariance of the CMB spectrum might reflect approximate conformal symmetry in a dual description. If so, the CMB would be a boundary correlator written across the sky. The conceptual payoff is sharp, and it reframes beginning without requiring a prior era. If the fundamental description has no bulk time in the usual sense, then before can be reframed as outside the bulk description. The beginning becomes a coordinate artifact of the emergent spacetime, not a boundary of the underlying theory. That does not make the Big Bang unreal, but it changes what kind of thing it is. It becomes like the edge of a map, not the edge of the world. Holography also changes what we mean by locality, which is one of the deepest intuitions physics has trained into us. In the bulk, events have positions and light cones, and influences propagate at finite speed. In the dual theory, the same physics can be encoded non-locally, spread across boundary degrees of freedom. The universe can be local in appearance and non-local in its foundations, without allowing causal paradoxes. The non-locality is structured, constrained by the duality's rules. It is not a loophole for faster-than-light messaging, but a reorganization of information. This is not license for anything goes speculation, and the documentary must keep that boundary firm. Dualities are rigid, and they constrain what is possible, sometimes more tightly than ordinary model building. If our universe has a holographic description, it must reproduce the observed near-Gaussian, nearly scale-invariant perturbations. It must also preserve the success of general relativity at tested scales, from solar system dynamics to gravitational waves. A holographic origin is not an escape from data, but a different route toward it. There is also a practical question lurking behind the elegance. If the early universe is dual to a lower dimensional field theory, what are the degrees of freedom, and how do they evolve? How do we recover a classical spacetime with a small cosmological constant and stable matter? How do we interpret cosmic time and expansion in the boundary language? These are not rhetorical flourishes, but the core technical challenges. The promise is that a well-defined boundary theory might avoid singularities that plague bulk descriptions. Now we step into extra dimensions, where the Big Bang becomes an event in a larger space rather than a boundary of time. Brainworld scenarios picture our universe as a 3+1 dimensional brain embedded in a higher dimensional bulk. Standard model fields are confined to the brain, while gravity can leak into the bulk. This confinement is not arbitrary, but motivated by how open strings and gauge fields behave in certain string-inspired constructions. The result is a universe that feels four-dimensional to particles, yet is larger for gravity. In these models, the Big Bang can be reinterpreted as a collision or interaction between brains, and the imagery is almost cinematic. Two vast sheets of reality approach in an extra dimension, invisible to us except through gravity's behavior. The collision deposits energy into brain degrees of freedom, reheating the universe into a hot plasma. The bang becomes a transfer of energy, not an infinite density point. What looks like a singular start in 4 dimensions becomes a dynamical event in a higher dimensional arena. This connects back to ekpyrotic inspiration from Chapter 5, where smoothing can occur during a slow contraction-like phase. Ekpyrotic and cyclic brain models use a slow approach in the extra dimension, then a collision that creates the hot phase. The smoothing can happen before the collision, because certain fields can drive the universe toward homogeneity and flatness. The collision becomes the matching surface between phases, and the hot Big Bang becomes a reheating boundary. In these pictures, before is not a prior time in the same space, but a prior configuration in a larger space. Brainworld pictures also modify the Friedman equations at high energies, and this is where the models become testable in principle. Extra terms can appear, including quadratic energy density corrections and dark radiation-like contributions. These modifications can change early expansion rates, altering how quickly the universe cools. That affects nucleosynthesis and the CMB, because both depend on the timing of key transitions. The early universe becomes a laboratory for extra-dimensional dynamics, even if we never see the extra dimension directly. Now we address constraints, because extra dimensions are not free, and nature has already set many traps for careless models. If gravity leaks into extra dimensions, Newton's inverse square law can change at short distances. Laboratory tests constrain deviations down to sub-millimeter scales, limiting the size and geometry of extra dimensions. These experiments are delicate because they must separate tiny gravitational forces from electromagnetic backgrounds. Yet their results are powerful because they directly probe the idea that space might be larger than it looks. Cosmology adds further limits, and they are often even more restrictive because the early universe was sensitive to small changes. Big Bang nucleosynthesis constrains any change to the expansion rate at minutes, because it would shift helium and deuterium yields. The CMB constrains extra relativistic energy density, often parameterized as effective neutrino number. Large-scale structure constrains how perturbations grow, because gravity's strength and behavior shape the cosmic web. A Brainworld model must fit all these at once, not just one dataset. Brainworld models also face constraints from gravitational waves, which have become a new precision tool since the first detections. If gravitons propagate in the bulk, energy can be lost from the brain in the early universe. That loss can alter the primordial spectrum and the damping of modes, leaving fingerprints in the CMB or in stochastic backgrounds. Observations restrict how large such effects can be, even if the constraints are model-dependent. The key point is that gravity is now an observed messenger, not merely an inferred force, yet the door is not fully closed, and the surviving space is scientifically interesting precisely because it is narrow. Some models hide extra dimensions through warping, as in Randall, Sundrum scenarios, where the geometry suppresses leakage at accessible energies. Warping can make gravity appear four-dimensional over large ranges even if the bulk exists. Others push new effects to scales we have not probed, such as energies beyond current colliders. The result is a narrow corridor of viability, not a blank check for imagination. There is also a conceptual shift that brainworlds invite, even when the details remain speculative. If our universe is a brain, Then, the universe is not the whole arena, but a surface within it. That changes how we picture horizons, singularities, and even conservation laws. Energy conservation on the brain can look different if energy can flow into the bulk, though the full higher dimensional theory remains conserved. The Big Bang in this view is a boundary event for us, but not for the larger reality. Now we go deeper, because extra dimensions are still space-time, and some proposals say space-time itself is a phase, like a state of matter. The Big Bang then becomes a phase transition, a change of state, rather than a start. This idea does not deny that the universe was hot and dense, but it changes what space means at the highest energies. It suggests that geometry can be emergent, not fundamental, and that the earliest epoch may have been pre-geometric. The question becomes whether time itself is part of the emergent package. Phase transitions are familiar in physics, and their familiarity is part of the appeal. Water condenses, magnets align, and symmetries break as temperature changes, producing new collective behavior. In the early universe, we already believe in phase transitions in fields, such as electroweak symmetry breaking. The radical step is to apply this logic to geometry itself. If matter can change phase, why not spacetime, which in general relativity behaves like a dynamical entity? In geometrogenesis-style ideas, the high-energy regime is not a smooth manifold, and that is a profound departure from classical intuition. It is a pre-geometric phase described by quantum degrees of freedom that do not look like space. As the universe cools, collective behavior produces an emergent spacetime with approximate locality. Locality here is not assumed, but achieved, like the rigidity of a crystal emerging from interacting atoms. The smoothness of space becomes a macroscopic approximation, valid when coarse-grained over many underlying degrees of freedom. One active research theme ties emergence to quantum entanglement, which provides a quantitative way to talk about connectivity. In several contexts, spacetime geometry appears linked to entanglement structure, with area laws and tensor networks offering toy models. The idea is not that entanglement is mystical, but that correlations can encode adjacency. If two subsystems are strongly entangled, they can behave as if they are near in an emergent geometry. This is an attempt to derive space from relationships rather than from coordinates. In holography, this link becomes sharper, and it gains an equation that can be spoken aloud. The Ryu-Takayanagi relation connects entanglement entropy in the boundary theory to areas of surfaces in the bulk. That suggests geometry can be computed from entanglement data, at least in those controlled settings. Spacetime becomes a derived quantity, like pressure derived from molecules, and curvature becomes an emergent response. The implication is not that space is fake, but that it is constructed. If spacetime emerges, then the Big Bang could mark the condensation of a geometric phase, a moment when the concept of distance becomes meaningful. Before would refer to a regime where the word time does not apply in the same way, echoing Chapter 4's warning. The beginning becomes a crossover between descriptions, not a first tick of a universal clock. This is a subtle kind of humility, because it admits that our language may not reach the earliest regime, yet it also offers a path forward, because phase transitions can leave relics. Those relics would not necessarily be circles or hotspots, but changes in statistical structure. A phase transition can produce defects, correlations, or characteristic spectra, depending on how it proceeds. If the emergence of spacetime changes dispersion relations or initial states, it can imprint features in the power spectrum. If it changes the behavior of primordial gravitational waves, it can alter the tensor spectrum across frequency bands. The challenge is to translate pre-geometric dynamics into predictions for observables we can measure. The reward would be a test of the idea that geometry itself has a history. Now we pull the threads together, because this chapter is the climax, and must feel like convergence rather than a list. CCC says the beginning is the end, after a conformal rescaling that preserves causal structure. Holography says the bulk beginning may be a boundary description with no bulk origin. Brainworlds say the bang is a collision in a larger arena, with reheating as the visible flash. Phase change ideas say the bang is when spacetime becomes a useful concept, like a new state of matter. These frameworks disagree about ontology, and they disagree about what is fundamental, yet they share a discipline. They replace before with a mapping, a duality, a transition, or an embedding. Because naive time language breaks at extremes. They try to keep mathematics continuous where ordinary stories demand a hard edge. They also try to leave something observable, because physics without tests is only story. The question is whether any of these translations can be made unique enough to confront data. Now, we return to observational reality, because the universe has already judged many beautiful ideas with indifferent precision. CCC's CMB circles and Hawking points remain disputed, and future CMB polarization maps may tighten the statistics. Polarization adds independent information, and it can help separate primordial signals from late-time contamination. Holographic cosmology seeks distinctive correlators and non-Gaussian shapes predicted by dual field theories. Brainworlds predict modified gravity signatures and altered primordial spectra, especially at high energies. Phase transition and emergent spacetime ideas are harder to test directly, but they can still be constrained by what they would disrupt. If emergence changes the initial vacuum state, it can produce running, oscillations, or features in the scalar spectrum. If it changes causal structure, it could alter the consistency relations between scalar and tensor modes. If it introduces preferred scales, it could spoil the near-scale invariance that the CMB exhibits. Even absence of anomalies becomes a constraint, because the early universe appears remarkably simple. The key observational handles remain the same ones we have built across the series, and their power comes from their interlocking nature. The CMB power spectrum and its anomalies remain central, because they encode the statistics of primordial fluctuations. Non-Gaussianity and isocurvature constraints limit how many fields and mechanisms can contribute. Primordial B modes and the tensor to scalar ratio, if detected, would reveal the energy scale of early dynamics, the expansion history and the growth of structure test gravity over cosmic time. Short-range gravity tests and high-energy consistency check the extra-dimensional and modified gravity corners. Now we acknowledge the uncomfortable truth, because mystery without honesty becomes myth. Many of these ideas are underdetermined by current data, and some may remain so for a long time. The early universe is a one-time experiment, and cosmic variance limits the larger scales where some signatures live. Theoretical flexibility can also absorb anomalies, turning prediction into post-diction. That is not a moral failure, but a structural difficulty of cosmology. But the story does not end in resignation, because underdetermination can still be narrowed by sharper questions. The point of this descent is to sharpen what would count as decisive, and what would merely be suggestive. A clean detection of primordial gravitational waves would narrow inflationary energy scales and constrain alternatives. A robust model-specific non-Gaussian pattern could favour a particular mechanism over generic inflation, because different mechanisms produce different shapes. A confirmed deviation from general relativity at short distances would open the door to extra-dimensional gravity. A statistically solid, independently reproduced CCC signature would force a rethinking of cosmic beginnings, especially if it came with multiple correlated predictions. A successful holographic cosmology that predicts observed correlators from a lower dimensional theory would change what universe means in a foundational way. It would suggest that spacetime is not the stage but the performance. The most unsettling possibility is that several frameworks could fit the same data, leaving us with multiple consistent translations. If that happens, the question becomes what counts as explanation. Now we set up the finale by turning the central question into an experimental challenge, because the series is about measurement as much as meaning. What would it take to turn before from metaphysics into measurable physics? It would take a signature that is both hard to mimic and hard to erase, and a theory that predicts it without tuning. It would take cross-checks across datasets so that no single map or instrument carries the entire burden. It would take predictions that survive improved foreground models, improved simulations, and improved statistics. The finale will not pick a winner by preference, because preference is not a cosmological parameter. It will ask which frameworks survive contact with data and which dissolve into language when pressed. It will return to the conclusion theme that has guided every chapter. The universe leaves clues in light, matter, and gravity, and our best hope is to read them until the beginning becomes testable. The deepest ideas are not those that sound profound, but those that risk being wrong. We end this chapter at the edge of a new kind of humility, where even the word time feels conditional. The Big Bang may be a start or a seam, or a shadow cast by deeper equations. Before may be a real physical chapter, or a question that dissolves when time becomes emergent. Either way, the universe has not stopped whispering, and the next chapter asks how we finally make it speak clearly. When the sky is both a boundary and a message, the act of listening becomes part of the science. We return to the opening hook because the word before still strains our physics and our language. If time is part of space-time, then before may be undefined, yet nature still leaves testable traces in what survives. First, we separate what is established from what is still inference, because cosmology is strongest when it labels its confidence. The hot Big Bang is secure from light element abundances in nucleosynthesis, the CMB's near-perfect blackbody curve, and the measured growth of structure. We can run the clock back to a hot plasma, then to a transparent universe at recombination, when electrons and protons finally formed neutral hydrogen. Visually, the rewind is almost cinematic. A sky that turns opaque, then white-hot, then so dense that even light is trapped in a churning fog. Yet the rewind still hits a wall where classical equations fail, not as a place in space, but as a regime. Near the Planck scale, quantum fluctuations of geometry should become unavoidable, so the smooth spacetime we draw on chalkboards stops being a reliable stage. Our question becomes operational because science advances by asking what can be measured, not what can be imagined. What would the universe look like? Meaning what signatures could survive into today's sky after billions of years of expansion? Which patterns would be robust enough to endure reheating, recombination, and the later clutter of galaxies and dust? Now we summarize the candidates, each with a different claim about before. Inflation offers a prologue that sets initial conditions, stretching microscopic quantum ripples to cosmic size, then reheats into the hot phase. Quantum creation replaces a classical earlier time with boundary conditions on a wave function, where beginning is a rule rather than an event. Bounce and cyclic models insist on a prior phase, with contraction or another branch leading into expansion, and with the hope that some memory crosses the turnaround. Conformal succession proposes a prior aeon, where the remote future maps into our beginning through a scale-free seam, so only angle and shape, not size, carries over. Higher dimensional events place the bang inside a larger arena, like brains colliding or geometry emerging from deeper degrees of freedom that only look four-dimensional to us. Now we state what the data actually support, without choosing a favourite story, because the sky does not care about elegance. Inflation is supported by the near-scale invariant, nearly Gaussian spectrum with a measured red tilt, first made precise by satellite maps, from COBE to WMAP to Planck. But inflation is not uniquely proven, because many mechanisms can mimic the same two-point statistics, especially if they are tuned to do so. Quantum gravity models remain largely unconstrained, because their distinctive signals are subtle, and often live on the larger scales where we have the fewest independent modes. Bounce and conformal ideas are plausible, but they must match the same acoustic peak coherence inflation fits well, including the phase relationships that come from a single, correlated origin. Extra-dimensional and holographic pictures are conceptually sharp, yet their cosmological predictions are still model-dependent, with details that shift as the underlying assumptions shift. This leads to the chapter's core discipline, which is defining evidence before we see it. Evidence means observables that are hard to fake and hard to erase. Even after astrophysical processes add noise, it means patterns with a predicted shape, amplitude range, and cross-checks across datasets, so a signal cannot hide in one instrument's quirks. The first decisive handle is the tensor-to-scalar ratio, R, through primordial B-mode polarization. In the visuals, this is a faint curl pattern laid over the CMB like fingerprints on frosted glass, distinct from the lensing-induced swirls we can partially subtract. A detection would anchor an energy scale and narrow inflationary model space dramatically, because gravitational waves tie directly to the expansion rate during the putative prologue. A stronger upper limit would push many simple inflation models into tension, while leaving room for low-scale inflation and many alternatives. It would also sharpen an old question. Did the early universe operate at grand unification energies, or at something far more modest? Either outcome is information, and either outcome changes what before is allowed to mean. The second handle is non-Gaussianity, because higher-order correlations remember interactions at birth, not just the power of fluctuations. Local, equilateral, and folded shapes point to different mechanisms, from multi-field conversion to non-trivial kinetic structure, and even to departures from the simplest vacuum state. Tight limits already rule out broad classes of models that predict large signals, and they quietly favour scenarios where the early dynamics were unusually simple. The third handle is primordial features in the power spectrum, including oscillations, cutoffs, and localized bumps. Features can encode a sharp event, a change in sound speed, or a bounce scale, like a brief stutter in an otherwise steady rhythm. They can also arise from initial state deviations, which makes the search both powerful and ambiguous, because the same wiggle can have more than one origin story. The fourth handle is curvature and topology, because a small residual curvature would reshape the meaning of early dynamics and the required duration of any smoothing phase. Inflation generically drives curvature towards zero, but not every scenario does so efficiently, and not every inflationary history lasts long enough. Better curvature constraints sharpen the boundary between long inflation, short inflation, and non-inflationary histories, and they also constrain exotic global shapes that could leave matched circles or repeating patterns. The fifth handle is relic backgrounds, including extra light species, relic particles, and dark radiation. These affect expansion during nucleosynthesis and recombination, and they shift CMB damping and peak phases in ways that precision data can detect. Any confirmed deviation would be a clue that the early universe had hidden sectors, perhaps populated at energies far beyond anything we can reach in laboratories. Now we lay out the near-future observational program, because the finale is about how we actually listen. CMB Stage 4 will map polarization with far higher sensitivity and better lensing removal, turning the sky into a cleaner laboratory for primordial signals. Future satellite polarization missions can extend frequency coverage and control systematics that ground experiments cannot fully escape, especially the subtle polarization from our own atmosphere and instruments. Galaxy surveys will measure baryon acoustic oscillations and the growth rate across cosmic time, using millions of galaxies as markers in a three-dimensional map. They will also tighten constraints on primordial non-Gaussianity through scale-dependent bias on very large scales, where the imprint is strongest. Large-scale structure becomes a second sky, with different noise and different systematics, and with a timeline that the CMB alone cannot provide. 21 Scimitar cosmology aims to map neutral hydrogen through the dark ages and cosmic dawn, when the first stars and black holes began to sculpt the intergalactic medium. It could access far more modes than the CMB, potentially beating cosmic variance on certain primordial statistics simply by surveying an enormous volume. It is also technically brutal, because foregrounds are bright and calibration must be exquisite, and because the signal is a whisper under a shout. Gravitational wave backgrounds add a new channel that does not rely on photons at all, which matters because photons last scattered when the universe was 380,000 years old. Pulsar timing arrays probe nanohertz bands where some early universe sources could rise above astrophysical confusion, revealed as correlated timing shifts across the galaxy. Space interferometers like LISA and future missions probe millihertz bands, where phase transitions, cosmic strings, or blue spectra could appear, turning the vacuum itself into a historical record. Now we confront the limit that no instrument can remove, which is cosmic variance. On the largest angular scales, we have only one realization of the universe, so some anomalies may remain forever suggestive, never decisive. This forces a probabilistic posture, where we ask how typical our sky is under each hypothesis, rather than demanding a courtroom certainty. We compare models by likelihood and complexity, not by absolute proof, because the data are finite and the theories can be flexible. Model selection under uncertainty becomes part of the scientific method, not an admission of defeat, and it has a long history in cosmology's debates. A model must predict more than it can flexibly absorb, or it becomes immune to learning. Beautiful perhaps, but scientifically inert. The goal is not a perfect story, but a constrained one that risks being wrong, because only risk buys information. And as the constraints tighten, the space of plausible befores narrows, even if it never collapses to a single line. Now we return to the meaning of look, because the word has been carrying two jobs. When spacetime is classical, look means a picture of earlier light, literally older photons arriving at our telescopes. When spacetime may not exist, look becomes a metaphor for reconstructing a mathematical state from its observable consequences, like inferring a hidden mechanism from the pattern it leaves behind. So the most defensible answer is careful and specific, because it respects what the evidence can actually bear. The Big Bang marks the start of the hot expanding phase we can test with high confidence. from nuclear reactions to plasma acoustics to the cooling of radiation. Whether there was a prior reality depends on the correct theory of quantum gravity and the dynamics that connect it to our observable branch. Inflation could be that connection, a prologue that hides earlier details while leaving a tensor trace and perhaps faint non-Gaussian scars. Quantum creation could mean there is no classical before, only a boundary condition that makes time emergent, with causality itself becoming a derived concept. A bounce or cycle could mean before is literal, with cosmic memory surviving as features, non-Gaussian fingerprints, or a distinctive gravitational wave spectrum that rises where inflation would be quiet. Conformal succession could mean before is another aeon, with only scale-free information crossing the seam, so the universe passes the baton without passing a clock. Higher dimensional events could mean the bang is a transition in a broader arena, where our four-dimensional time is not the whole story, only the slice we inhabit. Each option changes the grammar of origin, but each is constrained by the same sky, and by the same demand that predictions meet data. Now we close where we began, with honesty that keeps the mystery intact. The universe may be finite in age, cyclic, or one bubble among many, and those possibilities are not just philosophy, because they imply different observable residues. In every case, the only surviving testimony is written in patterns we can still measure, in light, matter, and gravity, faint, statistical, and yet remarkably precise. Before the Big Bang may be a real chapter, or a question that dissolves when time becomes quantum, and we should be prepared for either outcome. Either way, the universe keeps whispering through subtle correlations, and the last clue is that the beginning is not beyond science. It is waiting in the faintest structure of the sky, where the oldest information is also the most delicate. We followed the hot Big Bang back to its last reliable landmarks, redshifts and element abundances, the cosmic web, and the CMB's faint microkelvin grain. At the Planck wall, our equations stop describing a place and start describing their own limits. So we tested rival prologues by asking what scars they could leave. Inflation offers a smooth prelude that seeds structure with stretched quantum noise, yet it raises its own origin puzzles, while bounces, cycles, conformal stitching, and holographic or extra-dimensional beginnings all gamble on some form of cosmic memory. That memory is the real battleground, because a bounce must carry phase correlations, non-Gaussian fingerprints, or tensor spectra through a violent bridge without scrambling them into generic noise. Cyclic stories must also pay the entropy bill, explaining how low gravitational entropy returns, and whether it is diluted, exported, or redefined across black holes and horizons. Conformal pictures push the wager further, claiming the remote future can be rescaled into a new beginning, but only if the seam rule is precise about what survives, like cones, curvature, or subtle patterns in polarization. And every framework faces the same demand to predict hard-to-mimic correlators rather than flexible narratives, then survive cross-checks across instruments, bands, and statistical look-elsewhere traps. In the end, the universe does not reward the prettiest origin story. It rewards the one that keeps making risky predictions and keeps passing. The decisive clues are not philosophical, they are specific. Primordial B modes and a tensor-to-scalar ratio that cannot be faked by late-time dust. Non-Gaussian shapes that betray a bounce's entropic conversion, or an inflaton's interactions, power spectrum features that match across temperature and polarization, curvature or topology that refuses to average away, and relic backgrounds, gravitational waves, dark radiation, or light species that appear in more than one dataset. If B modes arrive with the inflationary consistency relations intact, the prologue looks like accelerated expansion. But if tensors stay absent while local non-Gaussianity or blue-tilted gravitational waves emerge, the balance shifts toward contraction, bounces, or more exotic beginnings. If CCC's circles or Hawking points ever survive independent pipelines, polarization correlations, and reproducible statistics, they would demand a companion signature that connects them to a concrete seam, not a pattern hunt. And if holographic or emergent spacetime ideas are to count as explanations rather than metaphors, they must name the correlators they change and the tuning they refuse to use. All of this happens under a quiet constraint: cosmic variance, which means the sky gives us only one realization of the universe's dice roll. So the standard of proof cannot be a single anomaly, but converging evidence, the same imprint seen in different observables, at different scales, with different systematics, and with predictions that were written down before the data arrived. That is how before becomes physics, by narrowing the space of stories until one remains stubbornly consistent, and the others run out of places to hide. What we called the Big Bang, then, is not a fireball at the centre of space, but the earliest hot chapter our tested laws can narrate. Beyond it may be inflation's shadow, a quantum boundary condition with no earlier time, a rebound from contraction, an aeon stitched by conformal geometry, or a deeper description where space-time is an emergent bookkeeping device. The common thread is that each proposal must answer the same question in its own language: what is the clock, what is the initial condition, and what survives to be observed. So the story closes where it began, at a wall that might be a door. The opening question was, if there was no time, what could before possibly mean? And why does the cosmos seem to remember something earlier? Now we can reframe it more carefully. Before is meaningful only if there exists a physical variable that orders events, and a mechanism that carries information into the hot beginning. If time truly becomes quantum or emergent, then before dissolves into boundary conditions. But the universe can still remember, because those conditions shape the spectrum of fluctuations we measure today. In that sense, the universe's first chapter is not hidden behind a curtain. It is written in correlations, tiny alignments of light, matter, and gravity that survived everything that tried to erase them. And whether the answer is an inflationary prologue, a bounce with selective memory, a conformal handoff between eons, or a deeper holographic script, the beginning will become real only when it becomes falsifiable. The final thought is this: the Big Bang may be the start of time, or it may be the moment time changed its rules. Either way, the cosmos keeps offering evidence, and it is up to us to learn how to read it. When we finally do, before the Big Bang will stop being a phrase at the edge of language and become a measurable feature of nature. If you want to follow the next clue, watch the polarization maps, the 21-centimeter sky, and the gravitational wave background, because the universe's earliest memory is most likely hiding there. The Big Bang is still the edge of what our current laws can explain, but it may not be the edge of physical history, only the edge of classical time. Before either becomes a real earlier phase that leaves hard-to-fake scars, or it dissolves into quantum boundary conditions, yet both possibilities can still imprint the sky. The universe may not let us stand outside time and watch the beginning, but it does let the beginning leak forward in patterns. In those faint fingerprints, light, matter, and gravity, we may eventually find not just an origin story, but an origin test. As new surveys arrive, demand predictions that can be cross-checked across temperature, polarization, galaxies, and gravitational waves, because that is how the wall becomes a door.